Hello, and welcome to Sleepy Science. Tonight, we are going to explore a disturbing possibility. What if the reality you experience is only a small window into something far greater? The universe may extend beyond everything we can observe, while your brain quietly constructs the world you believe you see. Across 30 strange and calming questions, we will explore space, time, consciousness, and the deeper mystery beneath reality itself. Before we begin, tell me in the comments where you are listening from and what time it is there. And don't forget to like the video and subscribe for more calm, mind-opening science. Now let the day fade away and let us begin. Why the universe may be bigger than reality itself. There may be more universe beyond the edge of every possible observation than there is within everything humanity could ever see. That idea sounds almost contradictory because we often use the word reality to mean the totality of what exists. But in cosmology, the reality available to us is limited by something more fundamental than technology. The distance information has been able to travel. Every signal we receive, whether from a nearby planet or a remote galaxy, must cross space before it can reach us. This creates a cosmic horizon, a boundary beyond which events cannot currently affect Earth. It is not a wall standing somewhere in the darkness, and there is no reason to think matter suddenly stops there. It is simply the farthest region from which information has had enough time to arrive. Beyond that horizon, space may continue for an enormous distance, perhaps without end, carrying regions that belong to the same universe but remain outside our observable reality. Cosmologists investigate this possibility by studying the large-scale shape of space, the distribution of ancient radiation, and the patterns left by the universe's early evolution. So far, the cosmos appears extremely uniform across the widest distances we can measure. This suggests that the visible region may be one small sample of a much larger structure, rather than a unique island surrounded by nothing. Yet science must remain careful. No telescope can photograph what lies beyond the boundary from which light has reached us, so anything said about those regions is an inference based on tested models, not a direct observation. The deeper mystery is that the inaccessible universe may not merely be far away. Parts of it may remain permanently unreachable. As space expands, sufficiently distant regions can recede in such a way that signals emitted there will never arrive here, even across an unlimited future. Those places could be physically real while remaining absent from every human record. No message would reveal their galaxies, no instrument would measure their history, and no traveler could cross the growing separation. This forces a distinction that is rarely noticed in ordinary life. Existence is not the same as accessibility. Reality does not need to announce itself to you in order to exist. A region of space may contain events, structures, and entire cosmic histories while having no possible relationship with Earth. The universe could therefore be far larger than the domain in which the word real gains practical meaning for us. It may contain countless separated horizons, each surrounding a different observer who sees only a local portion of the whole. From every such location, the visible universe would appear centered on the observer. Not because that observer occupies a privileged place, but because every cosmic horizon is defined by where and when information is received. This means the universe visible from another distant region could include areas forever hidden from us, while excluding parts of the cosmos that we can see. There may be no single viewpoint from which the whole structure can be observed at once. The complete universe, if such a total description is even physically meaningful, might exist without ever becoming fully knowable to any mind inside it. And that may be the most important lesson hidden within its scale. The limits of human knowledge are not necessarily the limits of existence. Beyond every map is not automatically emptiness, and beyond every observation is not automatically unreality. You may live inside a small causal region of something vastly greater, a local circle of light surrounded by distances that will never answer back. The universe may not be hiding its true size from you. It may simply be built so that no observer can hold all of reality within a single view. Why your mind never experiences the universe directly. The world you feel around you is not the universe entering your mind. It is your brain's carefully controlled interpretation of signals arriving from beyond it. This distinction is easy to miss because perception feels immediate. A face appears to be simply there. A voice seems to exist exactly where you hear it. And the warmth of sunlight feels like a quality belonging to the outside world. Yet your brain never encounters faces, voices, or sunlight in their original physical form. Light reaches the retina as electromagnetic energy. Air reaches the ear as pressure changes. And contact with an object produces mechanical activity in the skin. Specialized cells convert these events into neural signals, and only after the signals have been sorted, compared, and interpreted does a conscious experience emerge. Your brain is enclosed within the skull, surrounded by darkness and unable to inspect the external world for itself. It must work like an investigator inside a sealed room, reconstructing what lies outside from messages delivered through the nervous system. Those messages are useful, but they are never complete. Human eyes detect only a narrow range of the light that exists around you. Your ears ignore frequencies other animals can hear. Your nose misses chemical information that can guide a dog across great distances. The universe contains far more detail than your senses were built to receive, because evolution did not design perception to reveal reality in full. It shaped organisms to notice what helped them move, feed, avoid danger, and survive long enough to reproduce. What you experience is therefore not an exhaustive portrait of existence, but a practical biological model. Even the qualities that seem most firmly attached to objects are partly created within you. A leaf does not contain greenness in the way it contains atoms. It reflects certain wavelengths of light, and your visual system turns that pattern into the experience called green. Sound is not floating through the air as music. There are vibrations that the brain transforms into pitch, rhythm, and voice. Sweetness is not a property that exists alone inside sugar. It is the result of molecules interacting with receptors and a nervous system assigning significance to the encounter. None of this means the external world is unreal. A stone remains capable of injuring you, and fire continues to transfer energy whether or not anyone is watching. But the stone as you see it, the pain as you feel it, and the flame as you experience its color are conscious constructions produced in response to real physical causes. The brain also does more than translate incoming information. It predicts what is likely to be present before all the evidence has arrived. Perception appears to involve a continuous negotiation between sensory signals and expectations built from earlier experience. When the signals are unclear, the brain leans more heavily on context. This is why a shape in a dark room may briefly become a person, why unclear speech becomes understandable after you learn what words to expect, and why two people can interpret the same expression differently. The brain is not passively recording a finished world. It is making informed guesses and correcting them as new information arrives. Visual illusions expose this process because they place familiar clues into unusual arrangements, causing the brain's normally reliable assumptions to produce a misleading result. Your blind spot offers an even quieter example. Each eye contains an area where the optic nerve leaves the retina, and no light-sensitive cells are present. Yet you do not normally see an empty hole in your vision. The brain fills the missing region using surrounding patterns and information from the other eye. It does this so smoothly that the invented continuity feels indistinguishable from direct sight. Perception also takes time. Signals must travel through nerves and pass through multiple stages of processing before they become conscious, which means the moment you experience has already begun in the physical world. The brain compensates for these delays by coordinating inputs that arrive at different speeds and presenting them as a single, stable scene. You feel as though you are living in direct contact with the present, but conscious awareness is closer to a continuously updated reconstruction of what has just occurred. This hidden work is not a weakness. Without selection, prediction, and compression, the amount of physical information surrounding you would be overwhelming. Your nervous system leaves almost everything unnoticed so that a coherent world can appear. It emphasizes edges, movement, faces, threats, language, and other patterns that have mattered throughout human life. In doing so, it gives you not reality without filters, but reality made usable. The unsettling question is whether a mind built differently would discover a world that feels equally complete, yet looks nothing like yours. An animal guided by magnetic fields, ultraviolet markings, or underwater pressure changes inhabits the same physical environment while experiencing another version of it. A sufficiently different intelligence might divide objects, time, and space in ways you could not easily imagine. Human experience is not the form the universe naturally takes when no observer is present. It is the form produced when a particular kind of brain meets a small portion of what exists. Science helps you move beyond some of these limits, but even scientific instruments do not remove interpretation. Telescopes, scanners, and detectors convert inaccessible events into numbers, images, and sounds that human minds can examine. They expand the range of signals available to you, while reminding you that knowledge always arrives through some method of translation. You may never experience the universe exactly as it exists apart from every nervous system, but you can study the distance between the world and your experience of it. You can learn which parts of perception come from external causes, which are shaped by biology, and which are altered by expectation. And perhaps this realization should not make your surroundings feel false. It can make them feel more extraordinary. Every color, voice, texture, and depth you know is the result of physical events being transformed into awareness inside living tissue. The universe does not simply appear before you. Your mind builds a place where a small part of it can be felt. You never experience reality without mediation. Yet through that imperfect inner construction, matter has become capable of noticing the world, questioning its own senses, and wondering what may exist beyond everything it was built to perceive. How space can expand without expanding into anything. Space is not growing into a larger emptiness. The distance woven into space itself is increasing. That single idea removes one of the most persistent misunderstandings about the expanding universe. In ordinary life, expansion always seems to require a surrounding area. Smoke spreads into a room, water fills a container, and an inflating object pushes into the air around it. So when astronomers say the universe is expanding, the mind naturally pictures a vast cosmic object swelling inside an even larger void. But modern cosmology does not describe the universe as an object sitting within another space. Space is part of the universe, not a container placed around it. Its expansion is an internal change in the relationships between distant locations. Galaxies that are not held together by strong local gravity become farther apart because the scale of the space between them changes over time. They do not need to fly through a pre-existing external emptiness. The path separating them simply becomes longer. A useful way to approach this is to picture a flexible grid with points drawn across it. As the grid stretches, every distant point becomes farther from the others, even though none of them must move across the grid in the usual sense. The analogy is limited because a real sheet stretches inside three-dimensional space, while cosmic space does not require a higher dimensional room around it. Still, it captures the central principle. Expansion can be a change in distance within a system, rather than motion into something outside it. In Einstein's description of gravity, space and time are not rigid backgrounds. Their geometry can bend, evolve, and respond to matter and energy. The universe is therefore not unfolding on a fixed stage. The stage itself can change. This is why distant galaxies generally appear to recede from us, and why more distant galaxies tend to recede more rapidly. It is not because Earth occupies the center of a universal explosion. An observer in another galaxy would see the same broad pattern, with distant galaxies moving away from that location as well. Every large region can appear central because the expansion happens throughout space rather than from one privileged point. The Big Bang is often pictured as matter exploding outward from a single location, but that image is misleading. According to the standard cosmological model, the early universe was not a small ball surrounded by darkness. Space itself was in an extremely hot, dense state everywhere, and as it expanded, the distances between regions increased. Asking where the Big Bang happened is therefore unlike asking where a bomb exploded. In the model, it happened throughout the universe because every present region traces its history back to that earlier dense condition. This also explains why expansion does not stretch everything equally. Your body is not slowly growing with the cosmos, and neither are atoms, planets, or most galaxies. Electromagnetic forces hold atoms and molecules together, while gravity binds solar systems and galaxies strongly enough to resist the faint expansion acting across those scales. Cosmic expansion becomes important, mainly across the vast distances between large groups of galaxies, where local binding forces are too weak to prevent the overall geometry from changing. Even light is affected during its journey through expanding space. As space stretches, the wavelength of traveling light can stretch with it, shifting toward the red end of the spectrum. Astronomers use this redshift as one of the major tools for studying cosmic expansion. The light does not lose energy because it is rubbing against a substance or becoming tired. Its wavelength changes because the geometry through which it travels evolves while it is in motion. This is one reason the expansion of space cannot be treated exactly like ordinary objects moving through a static environment. At sufficiently great distances, the space between us and a remote galaxy can increase at an effective rate greater than the speed of light without violating relativity. The rule that nothing locally travels through space faster than light remains intact. What changes is the amount of space between distant regions, and relativity does not impose the same simple speed limit on that large-scale geometric growth. There is also no confirmed physical edge where expansion is occurring, no advancing frontier pushing into an exterior void, and no known cosmic surface beyond which outside begins. The universe may be finite or infinite. Either possibility can be compatible with expansion. A finite universe would not necessarily need a boundary, just as a traveler can move endlessly across Earth's surface without finding an edge. Although cosmic space has a different number of dimensions and may possess a more complex shape, an infinite universe could also expand, not by becoming more infinite, but by increasing the distance between its points. Infinity describes the absence of a final extent, while expansion describes how the internal scale changes. The two ideas do not contradict each other. This is where everyday intuition begins to fail, because the human brain evolved to understand objects moving inside environments, not environments whose geometry can transform. We ask what the universe expands into because almost everything familiar needs an outside. Yet the question may be based on a category mistake, like asking what lies north of the North Pole, or what material a distance is made from. It assumes that the universe must behave like an object, when it may instead be the complete network in which physical locations and distances have meaning. Cosmology does not claim to know whether some deeper structure exists beyond our current description, but no external container is required to explain the expansion we observe. The evidence can be understood through changes in space-time itself, and once that idea settles, the expansion of the universe becomes less like an explosion and more like a quiet transformation of separation. Galaxies remain within the cosmos. Light continues along its path, and no visible wall moves outward. Yet across immense scales, the measure between distant places grows. The universe does not need somewhere else to go, because it is not traveling into a destination. It is changing the meaning of distance from within. Why consciousness feels like a window into reality. Your awareness has no visible frame, yet everything you know appears inside it. A sound enters, a face becomes familiar, a thought rises, a feeling changes the meaning of the room, and all of it seems to arrive in one open field called experience. This is why consciousness feels like a window into reality. It presents a unified scene while hiding almost all of the machinery that creates it. You do not feel neurons exchanging signals, visual regions analyzing edges, memory systems comparing the present with the past, or attention selecting one detail while suppressing another. You simply see the person, hear the sentence, and understand the moment. The process disappears, leaving only the result. Philosophers sometimes describe this quality as transparency. When you look through clean glass, your attention rests on the landscape rather than the glass itself. Consciousness behaves in a similar way. You normally notice what you are aware of, not the biological process of being aware. This creates the powerful impression that the world is laid directly before an inner observer. Yet neuroscience has found no single chamber in the brain where a complete picture is displayed and watched by a separate self. Instead, conscious experience appears to depend on widespread communication among many specialized systems. One region helps identify shapes, another supports language, another tracks bodily condition, and others contribute memory, emotion, movement, and attention. These processes often operate independently and unconsciously. A large amount of information is handled without ever becoming part of your experience. Your body adjusts posture, predicts the next sound in a sentence, regulates breathing, and prepares movements before you become aware of the work. Consciousness seems to arise when selected information becomes widely available across the brain, allowing perception, memory, decision-making, and action to influence one another. The global neuronal workspace theory describes one version of this idea. Many processes compete outside awareness, but some information becomes strong or relevant enough to be broadcast across a larger network. Once that happens, you can report it, remember it, compare it with a goal, and use it to guide deliberate behavior. The window of consciousness is therefore not equally open to everything. It is narrow, selective, and constantly changing. At this moment, you may be aware of these words, while the feeling of your clothing against your skin remains faint. The sensation was present, but attention did not place it at the center of experience. As soon as it is mentioned, it may suddenly enter the foreground. Nothing new had to touch your body. The organization of awareness changed. This selective quality is essential because the brain cannot treat every signal as equally important. Consciousness gives certain information temporary priority. It creates a place where competing needs can be compared. The desire to continue resting, the sound that might signal danger, the memory of something unfinished, or the plan guiding your next action. What feels like a calm view of reality is also a control system deciding what matters now. But the unity of consciousness remains mysterious. Color, movement, sound, bodily sensation, and emotion are processed in partly different ways, yet they usually appear as one coherent event. You do not experience the redness of a cup in one mental location, its shape in another, and the movement of your hand somewhere else. The qualities arrive bound together as a single scene. Researchers call this the binding problem. And although the brain's timing, connectivity, and recurrent communication appear important, there is still no complete explanation of how distributed activity becomes one experienced world. Disorders and experiments reveal how carefully this unity is constructed. In blind sight, some people with damage to parts of the visual system report that they cannot consciously see an object, yet they can sometimes guess its location more accurately than chance. The brain can process visual information and guide behavior without producing the ordinary feeling of seeing. In other cases, a stimulus can influence decisions even when a person has no conscious memory of noticing it. These findings suggest that information processing and conscious experience are not identical. The brain can detect, evaluate, and respond while the window remains dark to that information. Consciousness may therefore be less like the entire mind and more like a changing surface where only certain results become visible. This also explains why your inner world feels richer than what you can describe. You may sense the mood of a place before you can name the details producing it. You may know that a face is familiar without immediately remembering the person's name. Consciousness often receives partial conclusions from processes it cannot inspect. It gives you access to outcomes while concealing the steps. That concealment creates both efficiency and illusion. Because the hidden work is unavailable, thoughts can feel as though they simply appear. Decisions can seem to begin at the moment you notice them, and perception can feel like effortless contact with the outside world. Yet consciousness is not merely a passive screen. What becomes conscious can reshape what happens next. Holding an idea in awareness allows you to examine it, question it, connect it to distant memories, and resist an automatic response. Conscious attention can train skills that later become unconscious, and reflection can interrupt habits that would otherwise continue without inspection. The window does not reveal the entire structure of the mind, but it creates a space in which the mind can respond to its own activity. This may be one reason consciousness feels so central. Through it, the organism does not merely react. It can notice that it is reacting. It can experience uncertainty, consider alternatives, and recognize itself as present within a situation. Still, the feeling of looking out from behind your eyes should not be mistaken for proof that a separate observer sits somewhere inside the brain. The sense of being a witness may itself be another construction, produced when perception, bodily awareness, memory, and attention are organized around a continuing point of view. There is experience, and there is the feeling that someone owns the experience, but science has not yet fully explained how either emerges from physical activity. That unanswered question is what makes consciousness different from an ordinary window. A glass pane can transmit light without knowing what passes through it. Consciousness does not merely reveal a world, it gives the world presence. A sound is not only processed but heard. Pain is not only detected but suffered. Beauty is not only classified but felt. The mystery is not simply how the brain gathers information, but why some information is accompanied by an inner life at all. You may never see the hidden architecture that assembles each conscious moment, yet its silence is precisely what makes experience seem open and immediate. The machinery withdraws, the scene remains, and for a brief interval reality appears to be looking inward through you. Why the night sky is actually a view into the past. Every star above you is a message that began its journey before it became part of your night. The sky feels immediate because the light arrives now, but what it reveals belongs to another time. Light travels extraordinarily fast, yet the universe is so vast that even this speed cannot make distant events appear instantly. The moon is seen as it was a little more than 1 second ago. Sunlight reaches Earth after traveling for about 8 minutes. So the glowing surface you see is already an 8-minute-old image. From the nearest stars, light takes years. From the Andromeda galaxy, it takes roughly 2.5 million years, meaning you see that vast collection of stars as it existed long before modern humans appeared. The night sky is therefore not a single picture of the universe at one universal moment. It is a layered archive, assembled from many different ages. Nearby objects appear almost current, while more distant ones are shown deeper in their history. When astronomers point powerful telescopes toward extremely remote galaxies, they are not merely looking farther across space. They are examining earlier stages of cosmic development. Some galaxies appear smaller, more irregular, and more active because their light began traveling when the universe was young and large galactic structures were still forming. By comparing objects at different distances, scientists can reconstruct how galaxies changed, how generations of stars enriched space with heavier elements, and how the large-scale cosmos evolved over billions of years. A telescope does not reverse time or send anyone into the past. It simply collects old information that has only now arrived. This is an important distinction, because the past being observed is not stored in the sky like a permanent recording. Light continues outward after an event occurs, carrying limited information about that event through space. If some of that light reaches a detector, scientists can analyze its brightness, color, and spectrum to learn what produced it. From tiny shifts and patterns in starlight, they can estimate temperature, chemical composition, motion, and sometimes the presence of planets orbiting distant stars. The universe's history reaches us not as a written account, but as radiation that must be carefully decoded. Even the dark spaces between visible stars can contain ancient signals too faint for human eyes, but detectable by specialized instruments. Radio telescopes, infrared observatories, and X-ray detectors reveal different chapters of the past because cosmic objects emit many forms of radiation, each shaped by different physical processes. Dust that blocks visible light may allow infrared radiation to pass through, revealing regions where stars are forming. X-rays can expose violent environments around collapsed objects, while radio waves can cross enormous distances carrying evidence of gas, magnetic fields, and energetic events. In this sense, astronomy is a form of historical investigation in which the evidence never arrives all at once. It reaches Earth according to distance, scattered across wavelengths and separated by millions or billions of years. This also means there is no simple, universal picture of what the entire cosmos is doing right now. In relativity, distant observers may disagree about which separated events should be considered simultaneous, and no signal can provide an instant update from across the universe. The present is local. You can know what is happening near you with only a tiny delay, but the farther you look, the more the idea of a shared cosmic now dissolves. The night sky hides this complexity behind its stillness. Constellations appear fixed, yet their stars may be separated by vast distances and may have no physical relationship beyond the pattern created from Earth's viewpoint. Their light left at different times, crossed different regions, and arrived together only because you happen to stand here at this moment. What looks like one peaceful ceiling is actually a collage of separate histories. And perhaps that is why looking upward can feel both intimate and unreachable. You are not watching the universe perform live. You are receiving delayed fragments from places you may never visit, each one carrying evidence of a moment that has already passed where it began. The sky does not show you where everything is now. It shows you what distance has allowed you to know. And every night, without making a sound, the past continues to arrive. How your brain creates a universe inside your head. Inside the darkness of your skull, a complete world is being assembled every waking second, filled with distance, depth, movement, objects, faces, danger, familiarity, and the quiet feeling that you are standing somewhere within it. This inner universe is not a tiny picture projected onto a hidden screen, and there is no single place in the brain where the entire scene can be found. Instead, what you call the world emerges from many systems working at once, each handling a different part of experience. Some regions detect edges and orientation, others track motion, recognize objects, locate sounds, monitor the position of your body, or connect the present with memory. Your experience feels whole because the brain combines these separate streams into one usable model. When you walk through a room, you do not consciously calculate the angle of every surface or the changing position of every object. Your brain builds a spatial map, updates it as you move, and predicts what should remain behind you when it leaves your field of view. This is why the world continues to feel stable, even though your eyes make several rapid jumps each second. During these movements, known as saccades, visual input is briefly disrupted, yet you do not experience reality as a sequence of shaking fragments. The brain suppresses much of the disturbance, compares new information with what was expected, and preserves the impression of a continuous environment. It is not recording a perfect film. It is maintaining a model strong enough to guide your next action. Deep within the brain, the hippocampus and nearby structures help organize where you are and how places relate to one another. Certain neurons become active when an animal occupies a particular location, while others appear to represent direction, distance, or the repeating structure of an environment. Together, these systems function less like a photograph and more like an internal navigation network. They allow you to leave a room, picture its layout, and return without seeing every part at once. The universe inside your head also contains a model of your own body. Your brain continuously estimates where your hands are, whether you are upright, how much space your body occupies, and which sensations belong to you. This body model is usually so reliable that you never notice it, but carefully designed experiments can confuse it. In the rubber hand illusion, for example, synchronized touches on a visible artificial hand and a hidden real hand can make some people begin to feel that the false hand belongs to them. The illusion does not prove that the body is imaginary. It reveals that the feeling of ownership is actively constructed by combining vision, touch, and timing. Even your sense of being located behind your eyes depends on the brain successfully uniting bodily signals into a stable point of view. When that integration is disrupted by injury, neurological conditions, or unusual experimental stimulation. People can experience parts of the body as unfamiliar or feel strangely displaced from their usual position. The inner universe is therefore not only a model of what surrounds you, it is a model of where you are within what surrounds you. Memory gives this constructed world continuity. A room feels familiar not simply because you see its present features, but because current patterns activate traces of previous encounters. The brain uses what it already knows to identify objects quickly, anticipate what belongs in a place, and notice when something has changed. This can be helpful, but it also means that expectation can fill in details that were never clearly perceived. In change blindness experiments, people sometimes fail to notice surprisingly large alterations in a scene when attention is interrupted. Their inner model preserves the overall meaning of the situation, while specific details disappear. You may feel that you hold a rich, complete image of everything around you, yet much of that richness is only available when attention returns to it. The brain does not need to store every visible detail at full resolution. It keeps a structured summary and retrieves fresh information when necessary. This efficiency is one reason your internal world can feel more complete than the information currently being processed. Emotion also changes its shape. Fear can make uncertain objects seem more threatening. Sadness can reduce the importance of rewards, and familiarity can turn an ordinary place into somewhere deeply personal. These changes are not decorative layers added after perception. Emotional systems help determine what receives attention, what is remembered, and what actions appear possible. The same street can become a path home, a place of danger, or a landscape of grief depending on the history carried into it. Your brain creates not only a world of objects, but a world of significance. It decides what is near enough to reach, important enough to notice, safe enough to approach, or urgent enough to escape. This is why two people can occupy the same physical space while living through very different psychological environments. Their internal universes are shaped by different memories, bodies, goals, and expectations. Yet the brain's creation is not arbitrary. It is constantly tested against incoming information. When predictions fail, attention is drawn to the mismatch, and the model must be revised. A movement in the corner of your eye, a voice where silence was expected, or a missing object in a familiar room creates surprise because reality has violated the brain's forecast. Learning occurs when these errors change what the system expects next time. In this way, your internal universe remains flexible. It is built from the past, but corrected by the present. Dreams reveal how much of this world-building machinery can operate without normal contact with the environment. During sleep, the brain can generate places, voices, movement, and entire situations using memory and spontaneous activity, often without recognizing that the scene lacks an external source. But waking life is different because sensory evidence continually constrains the construction. The brain is free enough to interpret, but not free enough to ignore consequences for long. A mistaken model is corrected by collision, failure, surprise, and the responses of other people. The inner universe survives because it remains connected to what lies beyond it. And this may be the strangest part of ordinary consciousness. You move through life inside a model that you almost never recognize as a model. It has no visible walls, no loading screen, and no obvious builder. It simply opens around you each morning, already arranged into objects, distances, memories, possibilities, and a body that feels like home. The world inside your head is not as vast as the cosmos, yet it contains everything you have ever personally known of the cosmos. Every horizon you have watched, every room you have entered, and every person you have loved has existed for you within this living construction. Your brain does not place a second universe beside the physical one. It creates the only organized world you can inhabit, a changing inner map where matter becomes location, sensation becomes meaning, and a silent network of cells produces the feeling of being present somewhere at all. Why the observable universe is only a tiny bubble. The universe you can observe is not a map of everything that exists. but a temporary bubble drawn around you by the paths information has managed to travel. Its boundary is often pictured as a distant shell, yet it is better understood as the limit of your cosmic history, the collection of places whose signals have had enough time to become connected with Earth. Because light moves at a finite speed, every observer occupies the center of a different observable bubble. A civilization billions of light years away would not see exactly the same universe you see. Some regions visible to them would lie forever outside your own view, while parts of your sky might be inaccessible to theirs. There is therefore no unique observable universe floating as a special sphere in space. There are countless overlapping horizons, each defined by an observer's location and moment in cosmic time. Your own bubble extends much farther than the simple age of the universe might suggest. The cosmos is about 13.8 billion years old, but the present distance to the most ancient regions we can observe is far greater than 13.8 billion light years, because space expanded while their signals were traveling. The oldest light available to ordinary telescopes comes from a time roughly 380,000 years after the early hot universe began expanding. Before that era, matter existed as a dense, electrically charged plasma. Light could not travel freely through it, because photons repeatedly scattered from charged particles, turning the young cosmos into something like a glowing fog. When the universe cooled enough for electrons and atomic nuclei to combine, light was finally able to move across space without constant interruption. That released radiation now detected as the cosmic microwave background, a faint glow arriving from every direction. It forms a kind of visual wall around the observable universe, not because nothing exists beyond it, but because earlier space was opaque to light. Looking at that radiation is like seeing the surface of an ancient cloud whose interior visible light cannot penetrate. This means even within our cosmic bubble, ordinary vision does not reach all the way back to the beginning. Scientists search for older information through other messengers. Neutrinos produced in the early universe may carry evidence from a time before light traveled freely, although they are extremely difficult to detect. Gravitational waves could, in principle, preserve traces from even earlier events, because ripples in spacetime do not scatter through matter in the same way light does. These possibilities reveal that an observational boundary depends partly on what kind of signal you use. The visible horizon, the neutrino horizon, and the gravitational wave horizon are not necessarily identical, yet all remain limited by causal contact. No instrument can obtain information from a region whose influence has never reached us. Why then call this accessible domain a tiny bubble? The honest answer is that no one currently knows how tiny it is compared with the whole. The phrase describes a serious possibility, not a measured ratio. Observations show that space is extremely close to geometrically flat across the region we can study. If the complete universe is curved and finite, its curvature must occur on a scale much larger than our observable domain, just as a small patch of an enormous sphere can appear almost perfectly flat. Models of cosmic inflation strengthen the possibility that our visible region is only a minute part of a much larger whole. Inflation proposes that, during a very early stage, space underwent an extraordinarily rapid expansion. A region once small enough for its conditions to become nearly uniform could have been stretched far beyond what is currently observable. The patch that later produced every galaxy we can see may therefore occupy only a tiny area within a far greater structure. Some inflationary models even allow expansion to continue elsewhere, creating many regions with separate observable horizons. These ideas are scientifically motivated, but they are not direct photographs of what lies outside our bubble, and they should not be presented as proven geography. The total cosmos could be merely much larger than what we observe, unimaginably larger, or infinite. Current measurements cannot choose decisively among those possibilities. The bubble also changes with time. As the universe ages, light from some regions that was previously unable to reach us can enter our observable history, revealing slightly more of the cosmos. But expansion complicates this growth. The ancient light arriving today may come from matter whose present location is now extremely distant. and some places we can see in their youth may never be reachable by any signal sent from Earth. Observation and physical access are not the same thing. You can receive an old message from a galaxy even when the evolving geometry of space prevents any new message you send from ever arriving there. In that sense, the observable universe is not a territory humanity possesses. It is a record of relationships that became possible before separation grew too great. Its apparent edge is not lined with darkness or marked by a final galaxy. As you look farther away, you encounter earlier cosmic eras until ordinary light reaches the hot, opaque beginning of its free journey. Beyond that, reality is hidden not behind a curtain placed in space, but behind the conditions of the past itself. This should change the way you think about the familiar image of the universe as a sphere filled with galaxies. That sphere is centered on Earth only because observation is centered wherever the observer stands. It is a local window shaped by time, signal speed, expansion, and cosmic history. The complete universe does not need to share its center, radius, or visible boundary. What you call the observable universe is simply the portion that has entered into conversation with this small region of space. And if the larger cosmos extends far beyond it, then every galaxy ever photographed, every ancient signal ever measured, and every structure placed on our grandest maps may belong to a single illuminated bubble inside an expanse whose scale no observer can fully hold. You are not looking at the universe from the outside and seeing how large it is. You are deep inside it, receiving a limited collection of messages, surrounded by a horizon that resembles an edge, only because everything beyond it has not found a way to speak to you. Why the present moment may be a mental illusion. The instant you call now has no clean beginning and no measurable edge inside your experience. It feels like a single point moving smoothly through time, separating what has already happened from what has not yet arrived. Yet the brain does not receive reality in perfectly synchronized packets. Light, sound, touch, balance, and signals from inside the body are processed through different pathways, each requiring different amounts of work. If consciousness simply displayed every signal the moment it became available, the world would feel fragmented. A person's lips might move before the voice seemed connected to them. A touch could appear separate from the sight of the hand causing it, and movements might break into disconnected stages. Instead, the brain gathers information across a brief interval and binds related events into one coherent moment. What you experience as the present is therefore less like a razor-thin line and more like a small temporal window, wide enough for the mind to combine change into meaningful patterns. A melody proves why such a window is necessary. No single musical note contains a tune. To hear melody, the mind must retain the notes that have just passed while connecting them with the note occurring now. If the past vanished completely at every instant, music would become a sequence of isolated sounds with no rhythm or shape. Speech works the same way. The meaning of a sentence depends on words that are no longer physically sounding, yet they remain briefly active within awareness, so the next word can complete the thought. Your experienced present quietly includes traces of what has just happened, which means it is not a pure instant at all. Psychologists and philosophers sometimes call this short span the specious present, the duration that feels immediately present even though it contains a small stretch of time. Experiments show that the brain can also reorganize events after they begin. In apparent motion illusions, two stationary lights flashing in nearby positions can be experienced as one light traveling between them. The brain does not merely register two separate flashes, it constructs a motion that was never physically shown. More surprisingly, later information can influence how an earlier event is perceived, a process often described as post-diction. The mind briefly holds uncertain signals open, waits for additional evidence, and then settles on the most coherent interpretation. This does not mean the brain freely rewrites reality or that time itself is imaginary. It means conscious experience is an edited summary rather than a moment-by-moment transcript. The same flexibility appears when people judge whether two events happened simultaneously. A flash and a sound produced together may not always feel perfectly aligned because vision and hearing have different processing demands. With repeated exposure, the brain can adjust what it treats as simultaneous, showing that the boundary of "at the same time" is partly calibrated rather than simply read from the world. Attention changes this calibration further. A threatening event, an unexpected sound, or a highly emotional experience can seem to expand in time because the brain records more detail or allocates more resources to it. During routine activity, long periods may appear to shrink because fewer distinctive changes are stored. Clock time continues normally, but psychological time stretches and contracts according to attention, memory, novelty, and emotion. This is why an anxious minute can feel longer than a peaceful one, while an absorbing hour can seem to disappear. The present you feel is not only built from sensory timing, it is shaped by what the brain considers important. Even the sense of smooth continuity may be constructed. Consciousness does not appear to examine every event with equal precision. Much of life is handled automatically, while awareness samples, organizes, and emphasizes selected changes. Yet it would be misleading to claim that the brain works exactly like a camera taking separate frames. Neural processing is continuous, overlapping, and distributed, and scientists still debate how this activity gives rise to the flow of experience. What is clear is that the felt present is not a simple copy of an objective instant. It is an achievement, a stable working model that allows you to understand movement, follow language, coordinate action, and recognize causes before the world changes again. Without this construction, you might receive more raw timing information, but you would understand less. The illusion is therefore not that events are unreal. The illusion is that awareness meets them at one perfectly defined point called now. In reality, your mind carries a small amount of the recent past forward, combines it with incoming evidence, and presents the result as a unified scene. The present feels immediate because the assembly process remains hidden. You notice the finished moment, not the joining of its pieces, and perhaps that is why now feels so certain while remaining so difficult to locate. The closer you try to examine it, the more it divides into memory, expectation, sensation, and interpretation. You live neither inside a frozen instant nor entirely outside the present, but within a moving span, the mind continually renews. A brief shelter of awareness where events become connected before they are released into the past. How light connects your mind to distant stars. A star can touch your awareness without ever touching your body, using nothing more than a few particles of light crossing an almost unimaginable distance. Somewhere far beyond Earth, pressure and temperature deep inside a star allow atomic nuclei to fuse, releasing energy that slowly works its way outward through layers of dense matter. The light that finally escapes from the star's visible surface is not a miniature picture of the star, nor does it carry a written description of where it came from. It carries energy, direction, wavelength, and polarization, physical properties that can survive a journey through space and later become information inside a living nervous system. Most of that light will never reach anything capable of noticing it. It spreads outward in every direction, thinning across a larger and larger region, passing through clouds of gas, dust, magnetic fields, and interstellar emptiness. A tiny fraction may eventually enter Earth's atmosphere, where some photons are absorbed and others are scattered. Those that reach the ground can be bent slightly by moving layers of air, causing distant stars to appear to flicker. The star itself is not rapidly changing brightness in that way. The twinkling is produced by Earth's atmosphere repeatedly shifting the path of its light before it enters your eye. When one of those photons reaches the retina, the connection becomes surprisingly intimate. It is absorbed by a light-sensitive molecule inside a rod or cone cell. In rod cells, which are especially important in darkness, the photon changes the shape of a molecule called retinol, which is held inside the protein rhodopsin. That tiny molecular change begins a chemical cascade, altering the electrical behavior of the cell. Unlike many neurons, photoreceptors are continuously active in darkness and reduce their release of chemical signals when light reaches them. The retina then compares activity across many cells, emphasizing contrasts, boundaries, and changes rather than sending a simple photograph toward the brain. By the time information leaves the eye through the optic nerve, it has already been organized into patterns that describe where light increased, where it decreased, and how the scene may be changing. Under ideal laboratory conditions, individual rod cells can respond to a single photon, although conscious detection usually requires several photons arriving in a suitable pattern. This means the faint point you call a star may begin in awareness through an extremely small number of physical interactions. The star does not need to send enough energy to warm your skin or move an object. It only needs to alter a few molecules in a dark, adapted eye. Your brain then combines signals from both eyes with memory, attention, and knowledge, turning a faint retinal event into the recognition that something exists far beyond your immediate surroundings. Yet ordinary vision reveals only a small part of what the light contains. To the unaided eye, a star may look like a simple white point, but its light carries evidence about the conditions in which it formed. When astronomers separate starlight into a spectrum, they find dark and bright lines produced when atoms absorb or emit specific wavelengths. These patterns act like physical signatures. Hydrogen leaves one set of lines, sodium another, calcium another. From them, scientists can identify elements in a star without collecting a sample or traveling anywhere near it. The overall color of the spectrum helps reveal surface temperature. Hotter stars tend to emit more strongly at shorter visible wavelengths, while cooler stars produce relatively more red light. Small shifts in spectral lines can show whether a star is moving toward or away from Earth. Periodic changes can reveal an unseen companion, including a planet whose gravity makes the star move slightly back and forth. Light can also carry information about rotation, magnetic activity, surface motion, and material between the star and Earth. A narrow beam entering a telescope may therefore contain an entire chain of clues, waiting to be separated and interpreted. The connection between mind and star is not mystical, but it is deeper than simple seeing. A physical event in one location changes matter in another location, and that change eventually becomes knowledge. The star affects a molecule in your eye. The molecule alters a cell. The cell changes the activity of a network, and the network contributes to a conscious thought. At no point does the star enter your skull, yet something that happened within its atmosphere becomes part of your inner life. The process depends on fragile conditions. If the photon had been absorbed by dust, scattered away by the atmosphere, or missed your pupil by a fraction of a millimeter, that particular chain would never have begun. Instead, after traveling across a region where almost every possible path ends unnoticed, it happens to meet a living receptor capable of responding. You may then give the event a name, compare it with a star chart, learn its temperature, or wonder whether planets orbit it. Light begins as radiation and ends as meaning, but the meaning was not traveling through space. The photon carried physical information. Your nervous system and your knowledge gave that information a place within experience. This is why looking at a star is both a measurement and a transformation. The eye measures the arrival of light, while the mind transforms that arrival into distance, identity, curiosity, and sometimes emotion. Instruments can extend the connection far beyond human vision. Detectors can register wavelengths your eyes cannot respond to, collect photons too sparse for you to notice, and preserve their patterns long enough for careful analysis. But even the most advanced observatory ultimately returns information to a human mind, where graphs become explanations and spectra become stories about stellar birth, structure, and death. The universe does not speak in language. It changes matter, and minds learn to read the changes. So when you stand beneath a clear sky and focus on a faint star, you are participating in a precise physical relationship. Energy that escaped a distant stellar surface has crossed space, survived the atmosphere, entered an opening only a few millimeters wide, changed the chemistry of your retina, and joined the electrical activity from which awareness emerges. The star remains remote, unreachable, and indifferent, yet for one quiet moment it becomes part of what you know. Across the distance between burning plasma and living tissue, light completes a bridge with no solid structure, connecting an ancient furnace to a thought that did not exist until the photon arrived. Why reality might be different, outside human perception. Reality may become unfamiliar the moment it is no longer arranged for a human-sized body moving at human speeds. Your everyday world is built around a narrow middle scale. Objects large enough to grasp, distances short enough to cross, and changes slow enough for the nervous system to follow. At this scale, a table seems solid, a stone seems still, and one event appears to cause another in a clean sequence. These impressions are useful and usually reliable, but they are not guaranteed to describe nature at every level. Move far enough away from ordinary experience and familiar categories begin to lose their authority. A cloud looks like a single object from the ground, yet from within it there is no clear surface, only countless droplets suspended in moving air. A coastline appears to have a definite shape on a map, but its measured length changes depending on how closely every curve is followed. Even the boundary of your own body is less absolute than it feels. Heat, moisture, bacteria, air, and chemical signals are constantly crossing it, while the atoms within you are gradually replaced through breathing, eating, and metabolism. The mind prefers stable things with clear edges because such categories make action possible, but nature often offers processes where perception gives you objects. This difference becomes even clearer when scale changes. A mountain seems motionless during a human lifetime, yet over geological time it rises, fractures, shifts, and erodes. A living forest may look like a collection of individual trees, while ecology reveals exchanges of nutrients, fungi, water, insects, and energy linking the system across generations. Neither description is false. The tree is real, and so is the network, but each becomes visible only when you choose a particular scale and ask a particular kind of question. Reality may not come divided into the exact units your mind naturally recognizes. The divisions may partly reflect what a human observer needs to track. Science repeatedly advances by discovering that an intuitive category was only a limited approximation. Heat once seemed like a substance flowing between objects, but it is better understood through the collective motion and distribution of particles. A solid object feels continuous, yet its behavior emerges from atoms, electromagnetic interactions, and quantum rules that cannot be pictured as tiny versions of familiar objects. A species may appear fixed when viewed over a few generations, while evolution reveals populations changing across deep time. What looks permanent at one scale becomes temporary at another. What looks separate becomes connected. What looks simple becomes the visible outcome of hidden interactions. This does not mean ordinary reality is an illusion. A chair remains a chair at the scale where sitting matters. The mistake begins only when a useful human description is treated as the final structure of existence. There is also no reason to assume that reality must be fully compatible with the habits of human thought. Your brain developed within a local environment where it was valuable to recognize faces, predict movement, remember social relationships, and avoid immediate danger. It was not shaped specifically to understand curved space-time, molecular probability, geological duration, or systems containing billions of interacting parts. When such ideas feel unnatural, that discomfort may reveal more about the history of the human nervous system than about the truth of the ideas. Mathematics, instruments, and careful experiments allow science to move beyond intuition by testing patterns that cannot be experienced directly. A detector can reveal a regularity no unaided sense would notice. A model can connect events separated by scales too large or too small for the mind to picture. Yet these tools do not give a view from nowhere. Every scientific description selects certain features and ignores others, depending on what is being measured. A weather model treats air differently from a molecular simulation. A medical scan describes a body differently from a biologist studying cells. Both can be accurate within their purpose. Reality may therefore be richer than any single representation, not because truth is purely subjective, but because complex systems can support several valid levels of description at once. The deeper question is whether human concepts such as object, boundary, cause, and identity reveal the universe's own natural divisions, or merely provide stable handles for a mind that must act quickly. Perhaps reality outside human perception is not darker, brighter, louder, or stranger in any simple sensory sense. Perhaps it is less divided than your experience suggests, more dynamic than your language allows, and organized through relationships that do not fit neatly into separate things. You may never step completely outside the human point of view, but you can loosen its grip. Each time science replaces a familiar picture with a more precise one, reality becomes less centered on what feels obvious to you. The world does not disappear when human intuition fails. It continues with structures, scales, and processes that were never required to resemble the environment your mind evolved to understand. And perhaps learning is partly the slow recognition that reality is not obligated to look familiar before it can be true. How black holes break our normal idea of space. A black hole does not merely occupy space like a dark object placed inside a larger room. It changes the structure of space so deeply that ordinary ideas such as direction, distance, and escape begin to lose their familiar meaning. Far from a black hole, space behaves much as you expect. You can move towards something, turn away from it, or choose another path. Near a black hole, however, gravity is not best understood as an invisible force pulling objects across a fixed background. In general relativity, mass and energy shape space-time itself, and objects follow the available paths through that curved geometry. Around a black hole, the curvature becomes so extreme that every possible outward route is gradually tilted inward. The event horizon marks the boundary where this change becomes irreversible. It is not a solid shell, a glowing surface, or a physical wall that an object crashes into. For a sufficiently large black hole, someone falling across the horizon might notice nothing dramatic at that exact moment. Local space could appear calm, and no alarm would announce that escape had become impossible. Yet the geometry would have changed in a decisive way. Beyond the horizon, all future directed paths lead deeper inside. Trying to escape would no longer be like swimming against a powerful current. It would be more like trying to move toward yesterday. The problem is not that an object lacks enough engine power. The problem is that outward no longer leads toward freedom in the way it does outside. In the simplest model of a non-rotating black hole, the inward direction takes on a strange inevitability. Before crossing the horizon, falling inward is one possible motion among others. After crossing, reaching smaller distances becomes as unavoidable as moving into the future. You can choose how you move locally, but you cannot choose a future that avoids the interior. This is one of the clearest ways black holes break the normal concept of space. A direction that once behaved like an ordinary spatial option becomes woven into the unavoidable progression of your path. The familiar image of a black hole as a funnel can help show curvature, but it can also mislead. A real black hole is not a dent in a flat sheet hanging inside another dimension, and objects are not pulled down the side of a cosmic drain. The funnel is only a simplified picture showing how distances can behave differently near a massive object. In three-dimensional space, the distortion surrounds the black hole from every direction. If you approached from above, below, or any side, the horizon would not become a hole cut into the universe. It would remain a boundary enclosing a region from which no signal can return. Distance itself also becomes less intuitive nearby. Two locations that appear close on a diagram may be separated by a geometry that makes travel between them very different from what a flat map suggests. Light rays that would normally spread outward can be bent into curved trajectories. At one special region outside a non-rotating black hole, light can orbit, although these orbits are unstable, and even a tiny disturbance can send the light either outward or inward. This region, often called the photon sphere, reveals how severely the black hole reshapes possible paths. Light is not slowing down below its normal local speed. Instead, the geometry redirects the route along which it moves. A distant observer may see multiple distorted images of the same background star, because its light has traveled around different sides of the black hole before arriving. What appears to be a single dark object can therefore act like an extreme gravitational lens, folding the visible sky into arcs, rings, and repeated images. A rotating black hole makes space stranger still. Most real black holes are expected to spin, and their rotation can drag the surrounding space-time with them. In a region outside the horizon called the ergosphere, it becomes impossible to remain completely stationary relative to distant space. Everything must move partly in the direction of the black hole's rotation. This frame dragging is not matter behaving like water in a whirlpool, though the comparison can be useful. It is the geometry itself acquiring a rotational character, carrying possible paths around with it. In principle, energy can even be extracted from this rotating region, because an object entering the ergosphere can split in a way that allows part of it to fall inward, while another part escapes with more energy than the original object carried. This does not make a black hole an endless power source, but it shows that rotation is stored not only in the matter that formed the black hole, but in the structure of space-time around it. Closer to the interior, differences in gravity across an object can become enormous. The side nearer the black hole may be pulled more strongly than the side farther away, producing tidal forces that stretch in one direction and compress in others. This is the origin of the term spaghettification, but the location where it occurs depends on the black hole's mass. Near a small black hole, destructive tidal forces could become extreme before the horizon is crossed. Near a supermassive black hole, the horizon can be so large that an observer might pass through it before tidal forces become immediately fatal. The horizon is therefore not defined by local violence. It is defined by the global structure of possible escape routes. At the center of the classical description lies the singularity, where the equations of general relativity predict that curvature becomes infinite. But scientists do not usually treat this infinity as a fully understood physical object. It is more likely a warning that general relativity has reached the limit of its usefulness and must eventually be replaced or completed by a quantum theory of gravity. We do not yet know what the deepest interior of a real black hole contains. The singularity might be replaced by a new structure, a quantum region, or something current physics has not learned how to describe. What is known is already unsettling enough. Black holes show that space is not a rigid emptiness through which matter simply travels. It can curve, trap, rotate, and rearrange the meaning of possible motion. Near one, a path outward can vanish without a wall appearing. Light can circle without any physical track, and the distinction between moving inward and moving onward can become strangely blurred. A black hole does not break space by tearing it apart. It breaks your ordinary intuition by revealing that space was never the passive container you assumed. It is an active part of the universe's structure, capable of becoming so distorted that the directions you trust no longer lead where they once did, and beyond the horizon. The very idea of turning back has no remaining place to go. Why time feels real, even if physics treats it differently. Time feels like the most undeniable thing in your life, because everything you love, lose, build, and remember seems to move in only one direction. Yet physics does not describe that movement as simply as your experience does. You feel time flowing from past to future, carrying each moment away and replacing it with another. But many of the fundamental equations used to describe nature do not contain a built-in river that moves forward. They describe how physical states relate to one another, and in many cases the same laws remain valid whether a process is imagined running forward or backward. A video of two billiard balls colliding may look physically reasonable in either direction, and the equations governing their motion do not clearly announce which version belongs to the future. Your experience, however, never feels reversible. You remember breakfast, but not tomorrow's dinner. A dropped cup breaks, yet scattered fragments do not leap from the floor and rebuild themselves. Your body grows older rather than younger, and every decision seems to close possibilities behind you. The key to this difference lies not in a universal clock forcing reality forward, but in the changing organization of matter, Large systems naturally tend to move from more ordered arrangements toward more numerous, less ordered ones. There are vastly more ways for a cup to exist as broken pieces than as one carefully assembled object, and far more ways for heat to spread through a room than to collect spontaneously in a single corner. This tendency is described through entropy, and it gives physical processes an arrow. The laws governing individual particles may often be reversible, but when enormous numbers of particles interact, overwhelmingly probable patterns appear. Heat spreads, structures decay, fuel is consumed, and records accumulate. The direction in which entropy increases becomes the direction you call the future. This helps explain why memory itself points backward. A memory is a physical record stored through changes in the brain. Forming it requires energy, chemical activity, and irreversible changes in neural connections. You can remember an earlier event because that event left traces in the present, altered synapses, photographs, written words, scars, fossils, or light captured by instruments. The future has left no such records because those interactions have not occurred. Your sense that the past is fixed and the future is open may therefore arise partly from the unequal distribution of evidence. The world around you is filled with traces of what has happened and almost none of what has not. Physics also treats time differently because there is no single universal clock shared by the whole universe. According to relativity, the amount of time measured between events depends on motion and gravity. Two clocks can begin together, follow different paths, and later disagree while both have operated correctly. A clock moving very rapidly can measure less elapsed time than one that remained relatively still, and a clock deeper in a gravitational field runs more slowly compared with one farther away. These effects are not philosophical curiosities. They have been measured with precise clocks and must be corrected in technologies such as satellite navigation. Your body carries its own path through space-time, and the time measured along that path is real for you. But it is not a master rhythm imposed identically everywhere. This means the universe does not possess one perfect present, sweeping across all locations at once. Observers moving differently can disagree about whether widely separated events occurred at the same time, even while agreeing on the events themselves. The familiar division into one shared past, one shared present, and one shared future is therefore not a basic feature of relativity. Some physicists describe space-time as a four-dimensional structure in which events are arranged by their relationships, rather than created one by a moving cosmic spotlight. This is sometimes associated with the block universe view, where past and future events are treated as parts of the full space-time structure. But physics has not proven that human experience is unreal, or that change is meaningless. The block description is an interpretation of how relativity represents events, not an explanation of why consciousness experiences succession. From inside your life, causes still precede their local effects, clocks still measure duration, and your choices still change what follows from your present conditions. Physics does not eliminate time. It separates several ideas that ordinary language blends together. There is duration measured by clocks, temporal order between connected events, the thermodynamic direction created by entropy, and the psychological feeling of flow. These are related, but they are not identical. Your internal sense of time is further shaped by the body. The brain tracks rhythms in movement, heartbeat, sleep, attention, and changing chemical states. Novel experiences often seem longer in memory because they leave more distinct records, while repetitive periods can collapse into a few similar traces. Fear may make seconds feel expanded because attention becomes intensely focused, while deep concentration can make hours disappear from awareness. None of this changes the clock on the wall, but it reveals that felt time is a biological interpretation of physical change. The brain does not contain a tiny clock that directly senses an invisible substance called time. It infers duration from sequences, bodily rhythms, memory, and change. If absolutely nothing changed, no motion, no thought, no decay, no heartbeat, no difference between one state and another, it is unclear what it would mean to detect time passing at all. A clock works only because something inside it changes regularly. A day is measured through Earth's rotation, a year through its orbit, and an atomic clock through repeated transitions in atoms. Time becomes measurable through change, even though physics uses time to describe how change occurs. This circular relationship is part of what makes the subject so difficult. You feel time as a force carrying you forward, while physics often treats it as a coordinate organizing events, or as a quantity recorded along a path. Both views capture something real, but neither alone explains everything. The equations reveal that duration is flexible, simultaneity depends on the observer, and many microscopic laws do not care which direction is called forward. Your life reveals that aging, memory, cause, loss, and possibility are profoundly directional. The bridge between them is built from entropy, records, biology, and the limited perspective of a mind moving through one sequence of events. Time feels real because change leaves irreversible marks upon you. Cells divide, memories accumulate, energy spreads, and each moment reshapes the conditions from which the next can arise. Physics may deny the universe a single flowing clock, but it does not erase the pattern that gives your existence direction. Perhaps time is not a river moving around you at all. Perhaps what you call its flow is the experience of being a changing system inside a universe where every new state carries traces of what came before, while the road ahead remains unwritten in the only place that matters to you, the life still waiting to be lived. Why you may never see reality as it truly is. The deepest barrier between you and reality may not be distance, darkness, or lack of technology, but the simple fact that knowing something always changes it into a form your mind can use. You never hold reality itself in your hands. You hold measurements, images, numbers, models, and descriptions, carefully built representations that reveal patterns while leaving the underlying thing partly hidden. A thermometer does not contain heat. It converts thermal activity into a readable scale. A telescope does not deliver a star as it exists. It gathers radiation and transforms it into signals that can be analyzed. A brain scan does not display a thought. It records changes in blood flow or electrical activity that scientists relate to mental processes. In every case, the world is translated before it becomes knowledge. This does not make science unreliable. It explains why science works through models rather than perfect replicas. A model is valuable because it leaves most of reality out and preserves the features needed to predict what will happen. A weather forecast ignores the exact motion of every air molecule, yet it can still describe storms. A map removes trees, smells, sounds, and texture, yet it can guide you across a city. The success of a representation does not mean it is identical to what it represents. It means the structure it captures is useful and testable. Reality may therefore be fully real while remaining impossible to picture in its complete form. At very small scales, this problem becomes unavoidable. To measure a particle, something must interact with it. Light may strike it, a detector may absorb it, or an electric field may influence its motion. Observation is not a magical act of consciousness, but a physical encounter, and every encounter reveals some properties while limiting access to others. Quantum theory goes even further by showing that certain pairs of quantities cannot both be assigned unlimited precision in the same physical state. This is not merely a defect in instruments that future engineers will repair. It is part of how the theory describes nature. The world may not possess every familiar property in a definite form before the measurement that defines it. If so, reality is not simply a hidden photograph waiting to be uncovered. The questions you ask help determine what kind of answer can appear. Even when measurements are precise, several explanations can sometimes fit the same evidence. Scientists compare theories by testing new predictions, searching for consistency, and preferring models that explain more with fewer unsupported assumptions. But evidence rarely arrives with its own final interpretation attached. The history of science is filled with theories that worked within a limited range and were later placed inside deeper frameworks. Newtonian mechanics remains extremely accurate for everyday motion, even though relativity gives a more complete account under extreme speed and gravity. Classical ideas remain useful for bridges and planets, even though quantum mechanics governs the microscopic world. A later theory does not always declare the earlier one meaningless. It reveals the conditions under which it was only an approximation. This suggests that knowledge may grow through increasingly accurate layers without ever reaching a final picture that cannot be revised. Language adds another boundary. Words divide experience into categories such as object, force, particle, field, cause, and self. These categories are powerful, but nature is not required to organize itself according to the grammar humans inherited. Physicists often rely on mathematics because ordinary images fail. An electron is sometimes described as a particle, and sometimes through wave-like behavior, but neither familiar picture captures it completely. These terms point toward patterns in experiments. They should not be mistaken for tiny everyday objects behaving in disguise. When a scientific idea becomes difficult to visualize, the problem may not be that nature is confused. It may be that visual intuition was built for medium-sized things moving slowly through ordinary environments. There are also truths that may be permanently unavailable from a particular position. You cannot observe a system from every possible perspective at once. You cannot recover every detail of an event after its traces have been erased. You cannot step entirely outside the universe to compare it with an independent original. Any description of the whole is made by observers who are themselves physical parts of that whole, using instruments made from the same matter they are trying to understand. This creates a quiet circularity. Reality produces minds. Minds construct theories, and those theories attempt to describe the reality that produced them. The circle does not make knowledge impossible, because predictions can still succeed and different observers can still agree. But it may prevent the complete separation between knower and known that perfect objectivity seems to require. Perhaps what science discovers most reliably is not reality as it would appear from nowhere, but the stable relationships that survive different methods of observation. The mass of an object, the frequency of light, the structure of DNA, and the behavior of gravity can be measured in repeatable ways even when the deeper nature of matter, life, or space-time remains open to interpretation. You may learn how reality behaves with extraordinary precision while still being unable to say what it ultimately is. That distinction can feel frustrating, yet it is also intellectually freeing. You do not need a final, absolute image in order to know something true. A ship can navigate by a chart that is not the ocean. Medicine can heal through models that do not explain consciousness. Physics can predict the motion of planets without answering why there is a universe capable of motion at all. Knowledge can be genuine without being complete. So perhaps you will never see reality as it truly is, because seeing it as it truly is would require a view with no scale, no perspective, no instrument, no language, and no observer shaping the form of the answer. Such a view may not exist. What you can have instead is a growing network of tested relationships, each one removing a little error without claiming to remove every mystery. Reality may always exceed the images used to describe it, but that excess is not a defeat. It is the reason inquiry continues. You stand within a world you cannot step outside, building clearer models from the traces it allows you to measure. And every honest answer reveals not only what has been understood, but the larger silence that understanding has not yet reached. How dreams prove the mind can build entire worlds. Each night, your mind can place you inside a city that was never built, introduce you to people who never existed, and make you fear events that never occurred, all while your body remains almost motionless in bed. Dreams do not prove that waking life is unreal, but they do demonstrate something remarkable. The brain can generate a convincing world without receiving the ordinary flow of information from the environment. During sleep, especially during periods of rapid eye movement known as REM sleep, many brain regions involved in vision, emotion, memory, and movement become highly active, while some areas responsible for careful judgment, logical consistency, and self-monitoring are less engaged than they are during wakefulness. This unusual balance helps explain why a dream can feel vivid while containing impossible events. A room changes shape, a dead relative speaks, or you arrive somewhere without traveling. yet the contradiction rarely stops the dream. The systems producing images and emotion remain active, while the systems that would normally challenge the scene may not be fully participating. The dream world, therefore, does not need to obey physical law perfectly. It only needs to remain believable long enough for the sleeping mind to continue inhabiting it. The brain does not usually create this world from nothing. It builds with fragments. A street from childhood may merge with a building seen briefly years later. The voice of one person may belong to the face of another. A recent worry may be placed inside an older memory, while a feeling with no clear source becomes the central atmosphere of the entire scene. Research suggests that dreams often combine recent experiences with older memories rather than replaying events exactly. The sleeping brain appears to reactivate and reorganize stored information, which may be related to memory consolidation, emotional processing, and learning, although no single theory explains every dream. This is why dreams can feel familiar without being recognizable. The pieces come from your life, but their arrangement is new. The mind acts less like a camera playing old footage and more like an editor working without a final script. It selects, blends, exaggerates, and connects material according to associations that may be emotional rather than logical. Fear can create a pursuer before the dream has decided who the pursuer is. Shame can construct an audience before it has chosen the place. Longing can produce a reunion even when the details constantly change. In waking life, external conditions restrict what can happen next. Walls remain where they are. People do not change identity in the middle of a sentence. And gravity does not disappear because the mood of the moment has shifted. In dreams, those restrictions are greatly weakened because the brain is generating much of the scene internally. The environment can transform as quickly as attention and emotion. This reveals an important feature of the mind. It does not need to design every detail in advance. A dream often creates only what becomes relevant. You may walk through a house without knowing what lies behind a door until you open it, and the next room appears with a sense of immediate reality. The sleeping brain can maintain the impression of a complete world even when many of its details are unstable or undefined. It creates enough structure to support the current experience, then updates that structure as the dream continues. Characters in dreams can also appear independent, surprising you with words or actions you did not consciously plan. This does not require another mind inside your own. Language, social expectation, memory, and emotion can generate responses outside deliberate control. The conscious dreamer receives those responses as though they came from someone else, because most of the processes producing them remain hidden. In waking life, thoughts also often appear before you know where they came from. But dreams make this hidden creativity more dramatic by giving those thoughts bodies, voices, and locations. Lucid dreaming reveals another layer. In a lucid dream, a person becomes aware that the experience is a dream while remaining asleep. Some lucid dreamers can influence what they do, test the environment, or signal to researchers through planned eye movements. Laboratory studies have even shown limited two-way communication with certain sleeping participants who were able to respond to simple questions while dreaming. These findings do not mean dreams are fully controllable. Even lucid dreamers can lose awareness, fail to change the scene, or be carried along by events generated automatically. But lucidity shows that self-awareness can sometimes return inside an internally created world, allowing the dreamer to recognize the construction without immediately waking from it. Dreams also reveal how strongly emotion can establish reality. A nightmare can increase heart rate, breathing, and stress responses even when no external threat is present. The danger is fictional, but the body's reaction is physical. Likewise, a joyful dream can leave comfort behind after waking, while grief experienced in sleep can remain for minutes or hours. The emotional systems of the brain do not dismiss an event simply because it was internally generated. If the scene activates the right networks, the feeling becomes real as an experience. Yet dreams should not be treated as secret prophecies or perfect messages from an unconscious mind. Their content can reflect concerns, memories, bodily sensations, and recent experiences, but symbols do not possess universal meanings that can be decoded with certainty. The same image can carry different significance for different people, or no deep significance at all. What dreams reliably show is not that every scene contains a hidden truth, but that the mind can produce immersive experience from incomplete and rearranged material. With the eyes mostly closed to the outside world, it can construct distance without physical space, characters without separate bodies, danger without an attacker, and movement while the muscles are largely prevented from acting out the dream. It can create a temporary reality, place you within it, and hide its own authorship so completely that you accept the world until something wakes you. Then the city disappears, the characters lose their voices, and the laws that seemed unquestionable a moment earlier collapse without leaving physical ruins. What remains is the knowledge that your mind does not merely store experience. Under the right conditions, it can become the architect, landscape, population, and witness of an entire world. And for a few sleeping moments, it can make that world feel like the only one that has ever existed. Why the universe has no center, yet everything expands. No matter where you travel in the cosmos, the universe will never reveal a single location from which all galaxies are fleeing, because cosmic expansion does not begin from a central point in space. This is one of the hardest ideas to accept, since every familiar expansion seems to have an origin. An explosion begins somewhere. Ripples spread from the place where a stone enters water. A crowd moves outward from a doorway. When astronomers observe distant galaxies receding in nearly every direction, it is natural to conclude that Earth must be close to the middle of a vast cosmic blast. Yet an observer living in another distant galaxy would see a similar pattern. From that galaxy, large numbers of other galaxies would also appear to be moving away, with the more distant ones generally receding faster. This would be true from almost any sufficiently large region of the universe. The pattern does not identify a hidden center. It reveals that the average distances between widely separated galaxies are increasing everywhere at once. A simple analogy is a loaf of raisin bread rising in an oven. As the dough expands, every raisin sees the others moving farther away. No raisin needs to occupy the center of the loaf's expansion, because the change occurs throughout the dough between them. A raisin farther away is carried apart by more expanding dough, so its separation grows more quickly than that of a nearby raisin. The comparison is imperfect, because the loaf has an outside and expands into the oven, while the universe is not known to require an exterior space. But it captures the essential relationship. Galaxies do not all need to be racing away from one special location. The large-scale fabric separating them can change uniformly. The familiar balloon analogy tells a similar story. Dots drawn on the surface of an inflating balloon move away from one another as the surface grows. For creatures restricted to that surface, there is no central point located anywhere on the surface itself. The geometric center of the balloon exists in another dimension, but it is not part of the two-dimensional world occupied by the dots. This does not mean our universe is literally the surface of a balloon, or that a higher dimensional center must exist. The analogy only shows how a space can expand without containing a center within itself. In cosmology, the crucial principle is that the universe appears broadly homogeneous and isotropic on very large scales. Homogeneous means that no enormous region seems fundamentally privileged over another when viewed across sufficient distances. Isotropic means that the universe looks statistically similar in every direction, once nearby structures and local motions are accounted for. Galaxies are not distributed perfectly evenly, of course. They gather into groups, clusters, filaments, and enormous walls separated by vast voids. But when astronomers examine the universe across hundreds of millions of light years, these local irregularities begin to average out. The cosmos resembles a landscape that looks rough from the ground, but increasingly uniform when viewed from high above. This large-scale sameness is what allows expansion to occur without selecting a single cosmic capital. If the universe had a physical center, observers near it and observers near an outer region would be expected to see dramatically different large-scale conditions. One might see galaxies receding evenly, while another might see most of them concentrated in one direction. Instead, The broad expansion pattern looks much the same from our location as it should from other typical locations. This is not proof that every point in the universe is identical, but it is strong evidence that Earth does not occupy a special central position. The confusion often begins with the Big Bang. It is commonly pictured as a tiny object exploding into empty space, sending matter outward from one location. In the standard cosmological description, however, the Big Bang was not an explosion at a place. It was an early state of the universe in which matter and radiation were extremely hot and dense across all the space described by the model. Every large region visible today traces its history back toward that earlier condition. If you could reverse cosmic expansion, galaxies would not all converge toward one address somewhere beyond the Milky Way. The distances between all widely separated regions would shrink together. The early dense state occurred here where Earth later formed, but it also occurred in the region now occupied by every distant galaxy. The Big Bang happened everywhere, not because an explosion covered every location after beginning, but because the locations themselves were once much closer together. This is why asking where the Big Bang occurred can be misleading. The question assumes there was already a large, empty cosmic room with one point chosen as the birthplace of matter. The theory instead describes the evolution of the room itself. There are still local centers throughout the universe. Earth orbits the Sun, stars orbit the center of the Milky Way, and galaxies move within clusters under gravity. These centers are real, but none is the center of the whole cosmos. They are centers of particular bound systems, like whirlpools within an ocean that has no single whirlpool at its center. Gravity can hold nearby matter together strongly enough that cosmic expansion does not pull those structures apart. The Milky Way is not expanding internally in the same way as the vast gaps between distant galaxy groups. The Andromeda Galaxy is even approaching us because local gravitational attraction is stronger than the general expansion between our two galaxies. Cosmic expansion is therefore not a command forcing every object to retreat from every other object. It is a large-scale trend that becomes clear only when the universe is viewed across enormous distances. There is also a useful frame of reference defined by the cosmic microwave background, the ancient radiation filling the universe. Earth moves relative to this radiation, producing a slight temperature difference between the direction we are traveling and the direction behind us. By measuring this pattern, astronomers can determine our motion relative to the average expansion of the surrounding cosmos. Yet this does not reveal a central location. It reveals a preferred state of motion, the frame in which the ancient radiation appears nearly equal in every direction. A cosmic rest frame is not the same as a cosmic center. You can change your motion relative to the expansion without changing your position into or out of some hidden middle. Another subtle point is that the expansion has no known outward-facing frontier. It is tempting to imagine the most distant galaxies as occupying the outer shell of a growing sphere, with younger galaxies nearer the middle. But distance in astronomy also means looking back through history. Faraway galaxies appear younger because their light began traveling long ago, not because they sit near a physical edge. An observer in one of those galaxies would regard the Milky Way's ancient light in much the same way. Each observer is surrounded by a view centered on their own location, but this is an observational center, not a geometric throne. You appear to stand at the center of your visible horizon for the same reason you always appear to stand at the center of the horizon on Earth. The boundary is defined by your viewpoint. Moving to another place moves the center of what can be seen, while the universe itself does not acquire a new center. Whether the entire cosmos is finite or infinite does not change this basic principle. An infinite universe can expand while remaining infinite, with distances increasing everywhere. A finite universe can also lack a center and an edge if its geometry closes back upon itself in an appropriate way. Scientists are still studying the universe's total shape, and no observation has established a final answer. But neither possibility requires a central point inside cosmic space. The deeper lesson is that the universe does not organize itself according to the images human intuition finds easiest. You are accustomed to standing inside objects, locating their middle, and measuring their outer boundaries. The universe may not be an object of that kind. It may be the complete system within which positions, middles, and boundaries receive their meaning. Everything can expand because the relationships between distant regions can change, while nothing needs to lead the motion from a privileged place. From Earth, the galaxies seem to withdraw into every direction. From another galaxy, Earth would be one of the objects appearing to withdraw. Neither observer is wrong, and neither is central. The expansion belongs to the space between them, not to a point behind one of them, and perhaps that is the quietest way the cosmos removes humanity from the center, without making our position meaningless. You are not standing near the origin of everything, watching creation escape into the distance. You are one local observer within a universe whose large-scale pattern can unfold around every location at once. A cosmos with countless viewpoints, countless apparent centers, and no single place entitled to call itself the middle of existence. How memory creates the feeling of a continuous self. You feel like the same person who opened their eyes yesterday, yet almost nothing in your body or mind remains perfectly unchanged from one moment to the next. Thoughts disappear, emotions shift, cells are repaired and replaced, attention moves, and each new experience alters the brain that receives it. What gives all of these changing states the feeling of belonging to one continuous life is not an unbroken substance hidden inside you, but a set of memory systems that connect the present person to earlier versions of the same organism. When you remember your childhood home, recognize your own name, know which people matter to you, or understand why a certain place makes you uneasy, the past is shaping the identity of the person standing in the present. Without those links, every morning would not feel like a return to your life. It would feel like an unexplained arrival inside a body surrounded by objects, relationships, and responsibilities whose meaning had vanished. Memory provides more than stored information. It gives events ownership. A photograph may show a child standing beside a birthday cake, but autobiographical memory allows you to say, "That child was me." The connection is strange because the child's body, knowledge, personality, and concerns may be very different from yours. There is no single physical feature that has remained untouched across the years. Yet memory creates a bridge across those differences, allowing the mind to treat widely separated states as chapters of one existence rather than unrelated lives. This bridge is built from several kinds of memory. Episodic memory allows you to revisit particular experiences, such as a conversation, a journey, or a moment of embarrassment. Semantic memory holds general knowledge about your life, including where you grew up, what work you do, and who belongs to your family, even when you cannot recall the exact moments in which you learned those facts. Procedural memory preserves skills such as typing, swimming, or riding a bicycle, often without requiring conscious recollection. Emotional learning can cause a person, sound, or location to feel safe or threatening before you remember why. These systems work together, but they can also separate. A person may lose the ability to recall events while retaining language, habits, preferences, and motor skills. This reveals that the continuous self is supported not by one memory archive, but by many overlapping forms of persistence. One of the clearest examples came from the patient known for decades as HM, whose real name was Henry Molaison. After surgery intended to treat severe epilepsy-damaged structures important for memory formation, he could no longer create most new long-term episodic memories. He could hold a brief conversation, but after enough time passed, the encounter could disappear from conscious recollection. Researchers might return, and he would meet them as though for the first time. Yet parts of his personality, childhood knowledge, language, and ability to learn certain physical skills remained. He could improve at a task across repeated sessions without remembering that he had ever performed it before. His case showed that memory is not a single faculty, and that conscious continuity depends especially strongly on the ability to carry recent experience forward. Each moment of his life still occurred, but many moments could not become stable parts of a remembered personal history. Another dramatic case is that of musician Clive Wearing, whose memory was severely damaged by illness. He often experienced the present as though he had only just become conscious, repeatedly writing that he was now truly awake for the first time. Yet he could still play music and recognize his wife with powerful emotion. His condition suggests that even when the ordinary timeline of the self is shattered, islands of identity can remain through skill, attachment, temperament, and older knowledge. Memory does not simply turn existence on or off. It binds some parts of a person across time while allowing others to disappear. Even in a healthy brain, however, continuity is less complete than it feels. You do not remember most days in detail. Entire weeks collapse into a few scenes. And the early years of life are largely absent because the brain systems and language needed for durable autobiographical memory were still developing. This childhood amnesia means that you lived through years of sensations, relationships, discoveries, and fears that no longer exist as accessible episodes. Yet you do not usually feel that the child who experienced them was a stranger. The consequences remain in language, attachment, habits, expectations, and emotional responses. Memory can preserve the influence of an event, even when the event itself cannot be recalled. Your continuous self is therefore not built only from scenes you can consciously replay. It also depends on traces that have become part of how you respond. At the same time, remembering is not the same as opening an untouched recording. When a memory is reactivated, it can briefly become open to change before being stored again, a process known as reconsolidation. New knowledge, present emotions, later conversations, and repeated retellings can alter details. This is why sincere people can remember the same event differently, and why confidence does not guarantee accuracy. But if memories are changeable, why does identity feel stable? Stability comes partly from repetition. Certain facts, relationships, values, and emotionally significant events are recalled again and again. Each rehearsal strengthens a familiar pathway through the past. Less important details fade, while recurring themes become easier to retrieve. Over time, the mind preserves not every event, but a structured sense of where you came from and what has mattered. This structure helps you predict your own behavior. You avoid foods that once made you sick, continue projects begun yesterday, trust people who have treated you well, and feel responsible for promises made by an earlier version of yourself. Society also depends on this memory-based continuity. A promise would mean little if the person who made it felt no connection to the person expected to keep it. Learning would collapse if the results of one day could not guide the next. Relationships survive physical absence because memories allow another person to remain psychologically present. Grief hurts partly because memory preserves a bond after new experiences with the person are no longer possible. Love also depends on accumulation. Not only the person before you now, but thousands of remembered interactions shaping what their presence means. Yet memory alone does not fully create the self. A newborn has no autobiography but is still a living subject. A person with amnesia does not become an empty body. The continuity of the organism, the body's needs, emotional tendencies, habits, social relationships, and the recognition offered by others all help preserve identity. Sometimes other people remember who you have been when you cannot. Families, photographs, messages, legal records, and familiar environments act as external supports for personal continuity. Human identity is partly carried outside the brain, distributed across the people and objects that hold pieces of a life. This becomes especially visible in dementia, where memory loss may gradually weaken a person's ability to recognize places, relationships, and personal history. Loved ones often feel that the person is disappearing, yet moments of humor, affection, music, or familiar gesture can remain. These moments reveal that the self is not located in one remembered biography alone. Still, memory is what allows the self to extend most clearly across time. It makes yesterday relevant to today and allows today to prepare for tomorrow. It turns consequences into lessons, repeated encounters into relationships, and biological survival into a life that seems to belong to someone. The feeling of being continuous is not produced because every moment remains present. It is produced because enough traces remain connected. your mind carries selected pieces forward, not as a complete archive, but as a living network of recognition, knowledge, emotion, and expectation. You are continuous not because you have stayed the same, but because change has left marks that later versions of you can inherit. And perhaps this is why losing a memory can feel like losing more than information. Each forgotten experience is a small doorway that no longer opens, a former version of you becoming harder to reach. Yet the life behind that door may still shape the way you speak, fear, love, and choose. Memory quietly gathers these surviving traces and tells the present mind that it did not begin today. It gives change a history, gives the body a past, and allows a sequence of temporary moments to feel like one person moving through time. Why empty space may be full of hidden structure. The emptiest place you can imagine may still contain the invisible framework that allows every particle, force, and physical event to exist. In everyday language, empty space means a region with nothing inside it. No air, no dust, no light, and no objects. Physics uses the word vacuum in a more careful way. A vacuum is a region from which ordinary matter has been removed as completely as possible. But removing particles does not necessarily remove the deeper physical systems that can produce them. Modern physics describes nature through quantum fields that extend throughout space. There is an electron field, electromagnetic fields, quark fields, the Higgs field, and other fields associated with the known particles of nature. A particle is not usually treated as a tiny independent bead placed into an otherwise blank container. It can be understood as a concentrated excitation of a field that is already present. An electron is an excitation of the electron field, just as a localized vibration can travel through a larger system without being separate from that system. The comparison is imperfect because quantum fields are not ordinary materials and do not require a mechanical substance beneath them. But it reveals the central idea. When all detectable particles are removed, the fields themselves do not disappear. They remain in their lowest possible energy state, known as the vacuum state. Lowest does not mean perfectly inactive. Quantum systems cannot always be reduced to complete stillness, because some physical properties cannot simultaneously possess exact motionless values. As a result, the vacuum contains unavoidable quantum uncertainty. Physicists often describe this through vacuum fluctuations, but the phrase is easily misunderstood. It does not necessarily mean that fully formed particles are constantly appearing from literal nothing and vanishing before nature notices. That popular image can be useful in limited calculations, but it should not be treated as a direct film of what empty space is doing. More accurately, quantum fields in their vacuum state possess measurable statistical behavior and correlations even when no ordinary particles are present. The emptiness has a ground state, and that ground state has structure. One of the clearest demonstrations comes from the Casimir effect. If two uncharged conducting plates are placed extremely close together in a vacuum, they can experience a small attractive force. The plates change the conditions that electromagnetic fields must satisfy in the narrow gap between them. Certain field patterns fit between the plates, while others do not, producing a difference between the quantum vacuum inside and outside the gap. The resulting force has been measured. It does not prove that space is filled with tiny hidden objects pushing the plates together, and there are several mathematically equivalent ways to describe the effect. What it shows is that the physical behavior of a vacuum can depend on boundaries. Empty space between two surfaces is not always physically equivalent to empty space far from them. The vacuum can respond to geometry. Another clue appears in atomic spectra. Electrons bound inside atoms occupy particular energy states, and the surrounding quantum fields slightly alter those states. One famous example is the Lamb shift, a tiny difference between energy levels that older theories predicted should be identical. Quantum electrodynamics accounts for this shift through the interaction between the electron and the quantum electromagnetic field. Even when no ordinary light is shining on the atom, the vacuum state influences the energies the atom can possess. The magnetic behavior of particles is also modified by quantum field effects, allowing predictions of extraordinary precision. These are not philosophical decorations added to physics. They are measurable fingerprints showing that what we call empty space participates in the behavior of matter. The Higgs field gives the vacuum an even more surprising role. Unlike many fields, the Higgs field is believed to have a non-zero value even in its lowest energy state. It does not switch off when particles are removed. Elementary particles interact with this ever-present field, and those interactions contribute to the masses they possess. This does not mean the Higgs field acts like a liquid slowing particles down, and it does not account for all the mass of ordinary matter. Much of the mass of protons and neutrons comes from the energy of the strong interactions binding quarks and gluons. Still, the Higgs field reveals that the vacuum can contain a persistent background condition that changes the properties of particles everywhere. Empty space is therefore not one universal blankness. Different physical theories can possess different possible vacuum states, each with its own characteristics. In the early universe, fields may have occupied states different from the ones surrounding us today. As the cosmos cooled, changes in those fields helped separate forces and determine how particles would behave. A transition between vacuum states can be compared cautiously to water freezing into ice. The underlying system remains, but its organized state changes and new properties appear. In particle physics, this process is associated with symmetry breaking. The laws may possess a broad symmetry, while the vacuum settles into a particular state that does not display all of that symmetry openly. The particles and forces observed afterward inherit properties from that choice. In this sense, some of the structure of the world may not arise only from objects placed into space, but from the state of the vacuum in which those objects exist. The strong nuclear interaction also gives empty space a complicated internal character. Quantum chromodynamics, the theory describing quarks and gluons, predicts a vacuum shaped by powerful interactions. Quarks are not normally isolated because the strong force behaves differently from familiar forces, becoming increasingly difficult to overcome as quarks are pulled apart. The vacuum associated with this theory contains patterns and collective effects that help determine the properties of protons, neutrons, and other particles. What looks like an empty interval between objects may therefore contain fields whose internal organization is essential to the existence of matter itself. Yet it would be misleading to call the vacuum a hidden ocean in the old-fashioned sense. 19th century physicists once proposed a substance called the luminiferous ether as a medium through which light waves traveled. Experiments and relativity showed that light does not require such a material background, and there is no detected preferred state of rest-filling space like invisible air. Quantum fields are not a return to that discarded ether. They obey relativity and do not provide an ordinary substance against which absolute motion can be measured. The vacuum has structure, but it is not a wind you could move through or a material you could scoop into a container. It is a physical state described through fields, symmetries, interactions, and the geometry of space-time. Gravity adds another layer. Even a region containing no matter can possess curved space-time, gravitational waves, or the influence of distant masses. According to general relativity, space is not simply a location where gravity acts. Its geometry is part of the gravitational phenomenon. A vacuum region around a star can still be curved, guiding the paths of planets and light. Ripples in space-time can travel through regions almost completely free of matter, carrying energy from violent cosmic events. Empty space may therefore have both quantum structure and geometric structure. Though scientists do not yet possess a complete theory that unites quantum fields with gravity, this missing theory is one of the deepest unfinished problems in physics. At extremely small scales, space-time itself may have properties that current concepts cannot describe. Some theories propose that space could emerge from more fundamental quantum relationships, rather than existing as the final background of nature. Others explore whether geometry is connected to patterns of quantum entanglement, information, or still unknown microscopic structures. These ideas remain active research rather than established fact, and no experiment has yet revealed a final layer beneath space-time. They matter because the vacuum sits at the meeting point of the two most successful frameworks in modern physics: quantum theory, which describes fields and particles, and general relativity, which describes gravity and geometry. Each works exceptionally well in its own domain, but they do not fit together completely under the most extreme conditions. The vacuum also creates a major cosmological puzzle. Calculations of quantum fields suggest that empty space should possess energy, and in general relativity, energy affects the expansion of the universe. Observations show that cosmic expansion is accelerating, a phenomenon commonly described using dark energy, or a cosmological constant. One possibility is that this acceleration is connected to vacuum energy. The problem is that straightforward estimates from quantum field theory do not naturally match the small value inferred from cosmology. The disagreement is enormous and remains unresolved. This is sometimes called the cosmological constant problem, and it may indicate that scientists do not yet understand the vacuum, gravity, or the relationship between them at a fundamental level. The emptiness between galaxies is therefore not merely an absence waiting to be ignored. It may be connected to the long-term behavior of the entire cosmos. Yet none of this means that unlimited usable energy can simply be extracted from empty space. Why your sense of now is already slightly delayed. By the time you become aware of this sentence, the physical events that produced it have already slipped into the past. Light had to reach your eyes, be absorbed by the retina, converted into electrical activity, transmitted through the optic nerves, separated into features such as shape and contrast, connected with language, and finally brought into conscious awareness. None of these steps is instantaneous. Depending on the type of information and the task involved, conscious perception can lag behind the outside event by tens or even hundreds of milliseconds. That delay is tiny compared with the length of a day, yet it is large enough for the world to change before you consciously experience it. A fast-moving ball can travel several centimeters during the time required for visual processing, and a car at highway speed can cover several meters before a driver completes a deliberate response. If your brain waited for a perfectly finished picture before preparing every action, you would always reach too late. Instead, the nervous system survives by predicting. It continuously estimates where a moving object is heading, what your body is about to do, and what the next instant is likely to contain. Your experience now is therefore not a simple photograph of the latest information received. It is a carefully updated estimate designed to keep you aligned with a world that has already moved ahead. This predictive work begins far below conscious thought. When you turn your head, the image of the room should sweep violently across your retinas, yet the world usually appears stable. Part of this stability comes from the vestibulo-ocular reflex, an extremely fast system linking the balance organs of the inner ear to the muscles controlling the eyes. As your head rotates, your eyes automatically move in the opposite direction, helping keep the visual scene steady. This response can begin before conscious awareness has time to analyze the movement. The brain also uses internal copies of movement commands, sometimes called corollary discharge, to anticipate the sensory consequences of its own actions. When you move your eyes voluntarily, the nervous system already knows that the retinal image is about to shift, so it does not interpret the entire world as suddenly jumping. Your sense of a stable present is maintained partly because the brain distinguishes changes caused by the environment from changes caused by you. The delay is not equal across the body. A touch on your toe must travel along a much longer path than a touch on your face, and signals carried by different nerve fibers move at different speeds. Some fast sensory fibers transmit information rapidly, while slower fibers associated with dull pain or temperature may take considerably longer. This is why pain from an injury can arrive in stages. An immediate sharp sensation may be followed by a slower, aching one, yet you rarely experience your body as a scattered collection of messages arriving at unrelated times. The brain organizes these signals into an event that belongs to one body in one situation. It does not erase the physical delays, but it builds a practical interpretation from them. Even vision contains several different processing speeds. Sudden movement, brightness, color, object recognition, and emotional significance are not all calculated in one place or completed at one moment. A threatening shape may begin influencing attention and bodily readiness before you can clearly identify what it is. You may jump at a coat hanging in a dark room and only afterward recognize that there was no person there. The reaction feels premature because rapid systems favored caution while slower analysis gathered more detail. In evolutionary terms, a nervous system that occasionally mistakes a harmless shape for danger may survive more often than one that waits for perfect certainty before responding. Your conscious present is therefore not always the brain's first response to an event. It is often the later, more organized understanding of activity that has already begun to guide the body. Motor control reveals the same hidden forecasting. When you reach for a cup, the brain must estimate the cup's position, the weight of your arm, the force needed, and the expected feedback from muscles and joints. Sensory correction arrives too slowly to control every tiny stage of the movement from scratch. Instead, the nervous system uses internal models that predict what the movement should feel like. Incoming feedback is compared with the prediction, and errors are corrected as the action continues. This is why practice makes movements smoother. The brain becomes better at forecasting their consequences, reducing the need for slow conscious supervision. A skilled musician does not deliberately calculate each finger position after hearing the previous note. An athlete does not wait to see exactly where a fast ball has reached before beginning to move. Their nervous systems use learned patterns to act toward a future location that has not yet been consciously seen. In this sense, the body often lives slightly ahead of awareness, while awareness experiences a reconstruction of what has just occurred. Experiments involving rapid visual events reveal this compensation. In the flash lag illusion, a moving object and a briefly flashed object can be physically aligned, yet the moving object often appears farther ahead. One explanation is that the visual system uses information about motion to estimate where the object is likely to be, while the sudden flash provides no similar history. Scientists continue to debate the exact combination of prediction and processing involved, but the illusion shows that visual experience is not determined solely by where signals began. Timing, motion, and expectation influence where an object appears to be. The brain's goal is not to preserve a perfectly delayed record. It is to produce an interpretation useful for action. This is also why your perception can feel immediate, even though the machinery behind it is slow. You have no independent, zero-delay version of reality with which to compare your experience. The processed scene is the only scene that enters awareness. You do not first witness the event and then notice the delay. The completed interpretation arrives carrying the feeling of being present. A film shown several seconds late still looks live to someone who has no access to the original event. In your case, the delay is much shorter and the system is constantly correcting itself, but the principle is similar. Consciousness receives a version of events after biological processing has already taken place, then labels that version now. This does not mean you are dangerously disconnected from reality. On the contrary, the delay is part of what allows the brain to create reliable perception. Neural processing extracts patterns from noise, compares present input with learned expectations, and coordinates action across a body whose parts are separated by different distances. A purely instantaneous awareness with no integration might be faster but less meaningful. It could register isolated changes without recognizing an approaching face, a spoken warning, or a hand reaching toward you. The brain sacrifices perfect immediacy in exchange for organization. Still, the idea has a quiet consequence. The conscious moment you inhabit is never the untouched front edge of reality. It is the newest version your nervous system has managed to assemble. While you feel yourself standing in the present, countless unconscious processes are already responding to events not yet fully known to you, predicting what will happen next and correcting predictions that failed. Your now is slightly delayed, but it is also gently pushed forward by expectation. It contains a recent past shaped into a scene and a near future quietly anticipated within it. You do not experience the world at the exact instant it occurs. You experience the brain's best attempt to remain synchronized with change, And because that attempt is so seamless, the delay disappears, leaving only the powerful feeling that you have arrived precisely on time. How the brain turns signals into a living reality. A silent electrical pulse traveling through nervous tissue contains no color, no voice, no fear, and no meaning, yet somehow billions of such pulses become the living world you inhabit. The brain does not receive experience in a finished form. It receives patterns of activity produced by sensory receptors, each pattern carrying only limited information about change. A receptor in the skin does not know that you are touching cold metal. It responds to pressure, temperature, or tissue movement. A cell in the inner ear does not hear music. It bends when fluid moves and changes the signals sent toward the brain. A retinal cell does not see a face. It reacts when light alters its chemistry. At the beginning of every experience, there is only physical interaction and a changing flow of electrochemical messages. The remarkable transformation begins as these messages pass through layers of neural processing. Early brain regions separate information into simple features. In vision, some neurons respond strongly to edges tilted in particular directions, others to movement, contrast, color, or changes in brightness. In hearing, different groups of cells respond to different frequencies, timing differences, and shifts in intensity between the two ears. Touch is mapped across brain tissue so that neighboring areas of the body are represented in neighboring neural regions. Though sensitive parts such as the lips and fingertips receive far more processing space than less sensitive areas. These systems do not create a complete reality independently. They extract fragments that later networks must combine. A moving person is not processed as one indivisible object from the beginning. Shape, direction, facial identity, emotional expression, and location are analyzed through partly separate pathways, then linked through coordinated activity. This is one reason brain injury can damage a surprisingly specific part of experience. Some people can see an object clearly yet cannot identify what it is. Others can recognize objects but struggle to recognize familiar faces, a condition called prosopagnosia. Some can describe the parts of a scene while failing to notice one side of space, not because their eyes are blind, but because attention no longer gives that side a place in conscious awareness. These cases reveal that the reality you experience is assembled from specialized operations that normally cooperate so smoothly their separation remains invisible. A major gateway in this process is the thalamus, a set of structures deep within the brain that receives and organizes much sensory information before it reaches the cerebral cortex. The thalamus is not merely a passive relay station. It helps regulate which signals are strengthened, which are suppressed, and how different brain regions communicate. Attention can alter this flow. In a crowded room, many voices reach your ears, but the brain can increase the priority of one conversation while pushing others into the background. The ignored voices still produce neural activity, yet they do not become equally vivid parts of your world. Reality feels rich and continuous, but its living quality depends on selection. The brain is constantly deciding what deserves detail, what can remain vague, and what must trigger action. Meaning begins to emerge when sensory activity connects with memory and value. A particular pattern of sound becomes your name because the brain has learned its significance through repetition and social experience. The smell of smoke becomes urgent because memory and emotion connect it with danger. The face of someone you love is not merely a visual arrangement of eyes, skin, and movement. It activates stored knowledge, attachment, expectation, and bodily responses. The same sensory signal can therefore create different realities in different minds. A dog barking may represent companionship to one person and threat to another. A hospital corridor may feel ordinary to a worker and terrifying to someone carrying a painful memory. The physical input may be similar, but the living experience changes because the brain interprets signals through the history of the organism receiving them. Emotion plays a central role in this transformation. The amygdala, insula, brainstem, hypothalamus, and other connected systems help evaluate whether something is harmful, rewarding, familiar, or important. They also monitor the condition of the body, heartbeat, breathing, hunger, muscle tension, temperature, and internal chemical balance. Your reality is therefore never constructed from external signals alone. It is mixed with information arriving from within. A rapid heartbeat can make an uncertain situation feel dangerous. Exhaustion can make a manageable problem seem overwhelming. Hunger can increase the visibility and value of food-related cues. The world feels different because the brain is not building a neutral description of the environment. It is building a world for a body with needs. Neuroscientists sometimes use the term interoception for the brain's sensing of the body's internal condition. Interoception contributes to emotion, mood, and the feeling that experience is happening to you, rather than appearing as detached information. A red light is not only registered, it may stop your movement. A threatening expression is not only classified, it may tighten your muscles. A warm voice is not only heard, it may calm breathing. Reality becomes living when signals are connected to the body's possible actions and consequences. The brain continuously asks, without words, what can be approached, what should be avoided, what can be ignored, and what must be remembered. Perception is therefore closely tied to action. The visual system represents objects partly in terms of what can be done with them. A handle suggests grasping, a stair suggests climbing, and an approaching object demands preparation. These possibilities are sometimes called affordances, opportunities for action offered by the environment relative to a particular body. A staircase is not the same reality for a child, an athlete, and a person with an injured leg. Its physical structure may be unchanged, but its practical meaning differs. The brain turns signals into a world by placing them inside a field of possible behavior. This is why perception can change when your intentions change. While searching for a friend in a crowd, faces become more important than clothing or architecture. While driving, movement at the edge of vision gains urgency. While listening for your name, a familiar sound can rise suddenly from background noise. The brain does not simply ask, "What is out there?" It also asks, "What matters for what I am doing?" Learning continually reshapes this process. A radiologist can notice subtle differences in a medical image that appear meaningless to an untrained viewer. A musician can hear timing and harmony that another listener does not consciously detect. A skilled birdwatcher can identify species from tiny differences in shape, call, or movement. Their sensory organs may receive similar inputs, but experience has changed the neural networks that interpret those inputs. Reality becomes more detailed in areas where the brain has learned which distinctions matter. This shows that perception is not fixed at birth. It is trained through attention, repetition, feedback, and culture. Language can also influence which differences become easy to notice and remember. The categories provided by words do not create the physical world, but they can sharpen the boundaries the mind uses to organize it. Once you learn the name of a pattern, it may become easier to see. Yet despite all this processing, no single neuron contains the complete scene. There is no known central screen where color, sound, memory, emotion, and bodily feeling are projected together for an inner spectator. Experience appears to depend on large networks exchanging information through recurring loops. Signals travel forward, backward, and sideways across the brain. Higher regions send expectations toward lower sensory areas, while incoming information corrects those expectations. This recurrent communication may help stabilize a perception long enough for it to become reportable, memorable, and available for decision. The exact biological conditions required for conscious experience remain unresolved, and scientists continue to debate competing theories. What is clear is that a living reality requires more than raw detection. Many signals influence behavior without entering awareness at all. The spinal cord can withdraw your hand from heat before you consciously feel pain. The brain can adjust posture, eye position, and muscle tension without asking permission. Familiar actions can unfold with little deliberate attention. Conscious reality seems to emerge only when selected information becomes integrated with a wider network involving memory, goals, emotion, bodily condition, and the capacity to guide flexible action. This is why a signal can exist in the nervous system without becoming part of the world you consciously know. The transition from neural activity to felt experience remains one of science's deepest mysteries. Researchers can trace pathways, measure timing, disrupt specific regions, and observe how perception changes, but they cannot yet explain why organized activity is accompanied by the redness of red, the ache of grief, or the intimacy of a familiar voice. They can describe the conditions under which experience disappears under anesthesia and returns during waking. But the bridge between physical processing and subjective feeling is still incomplete. That gap should not tempt us toward false certainty. It is honest to say that neuroscience explains many mechanisms of perception, while the existence of experience itself remains an open problem. Why the self may be a story the mind keeps updating. You may feel as though there is a single, finished person living behind your eyes, but the self you recognize may be closer to an ongoing story than a permanent object. The mind is constantly trying to organize scattered experiences into a coherent explanation of who you are, what you want, why you acted, and what kind of person will wake up tomorrow. This story is not written once and stored unchanged. It is revised whenever your behavior surprises you, when another person reflects a different version of you back, when a belief fails, or when a new role demands qualities you did not know you possessed. Psychologists sometimes call this the narrative self, the sense of identity created by arranging events, values, goals, and relationships into a personal account with an apparent beginning, direction, and meaning. The story does not need to be spoken aloud. It can exist as a quiet structure beneath thought, influencing what feels consistent with me and what feels foreign. You may describe yourself as patient, independent, cautious, generous, or unlucky. And once such a description becomes part of your identity, the mind begins sorting experience around it. Moments that support the story are noticed and remembered more easily, while contradictions may be explained away, minimized, or treated as exceptions. This does not mean you are deliberately lying to yourself. The brain is trying to preserve coherence. A person who sees themselves as kind may interpret a cruel remark as necessary honesty. Someone who believes they are rational may describe an emotional decision as carefully calculated. When action and self-image conflict, the mind often creates an explanation that allows both to remain connected. This process resembles what psychologists call cognitive dissonance reduction. When beliefs and behavior clash, people often adjust their interpretation to reduce the discomfort. The story changes just enough to keep the character recognizable. Neurology offers even more striking examples of this storytelling tendency. In some split-brain experiments, communication between the brain's hemispheres was surgically reduced as a treatment for severe epilepsy. Researchers could present information to one hemisphere without fully sharing it with the other. A participant might then perform an action influenced by information available mainly to the right hemisphere, while the language-dominant left hemisphere was asked to explain why the action occurred. Instead of simply admitting ignorance, the person could produce a plausible reason based on the information available to them. The explanation felt sincere even when it was created after the behavior had already begun. These findings led researchers to describe an interpreter function, especially associated with the left hemisphere, that tries to build a coherent account from incomplete evidence. This should not be simplified into the claim that one half of the brain invents the self, or that everyone has two separate personalities. The real lesson is subtler. The mind often explains its own behavior using partial information, and the explanation can become part of identity even when it was not the original cause. Confabulation reveals a related process in certain forms of brain injury or memory disorder. A person may confidently provide explanations or events that are inaccurate, not to deceive others, but because the brain fills missing information with a story that feels internally consistent. Healthy minds usually operate under stronger correction from evidence, yet ordinary self-knowledge is still imperfect. You often know what you did before you know exactly why you did it. Many motives compete beneath awareness. Habit, emotion, social pressure, bodily state, fear of rejection, desire for reward, and conscious thought may receive only the final result. It then turns that result into a sentence. I chose this because the sentence can contain truth, but it may not contain the whole causal history. The self-story is therefore partly retrospective. It watches the person act and then explains the person back to themselves. Yet identity is not only built from explanations of the past, it also works as a prediction about the future. When you say, I am not the kind of person who would do that, you are using a model of yourself to limit possible action. When you decide to become disciplined, brave, or forgiving, you are attempting to revise the model so that future behavior will follow a new direction. The brain benefits from such models because they reduce uncertainty. Instead of reconsidering every choice from the beginning, you can act according to values, habits, and roles already associated with who you believe yourself to be. A parent, teacher, friend, leader, or outsider carries expectations that guide behavior before deliberate thought is required. But these roles can also become prisons when the story grows too rigid. A person who has repeated, I always fail, may interpret each setback as proof and each success as luck. Someone who believes they must be strong may hide pain until they no longer know how to ask for help. The story becomes powerful not because it is objectively complete, but because it controls which evidence is allowed to matter. Social life is one of the main forces that edits this inner narrative. You learn who you are partly through how others respond to you. Praise can turn an accidental success into a lasting identity. Repeated criticism can make a temporary weakness feel permanent. Different relationships can call forth different versions of the same person. Confident among close friends, cautious at work, playful with a child, silent around someone associated with old shame. None of these versions must be fake. The self may be context sensitive, with different patterns becoming active in different environments. The mistake is assuming that one of them must be the hidden, authentic core while all others are performances. Human identity may be more like a repertoire than a single mask. What feels most like the real you may simply be the pattern that has been repeated most often, or supported by the most familiar surroundings. Brain imaging studies often find that thinking about oneself, remembering personal events, considering other people's minds, and imagining the future involve overlapping regions commonly associated with the default mode network. This does not mean scientists have located the self in one network, because identity depends on many systems across the brain. But it suggests that selfhood is linked to the ability to connect experiences across time, simulate possibilities, and place events into a larger personal context. The mind does not merely register what is happening. It asks what the event means for the person it believes you are. A rejection becomes evidence of unworthiness, a lesson in compatibility, or a random disappointment depending on the larger story surrounding it. The same event can reshape identity or pass through with little effect. What changes you is not only what occurs, but where the event is placed within the narrative. This updating can happen gradually, but sometimes one experience forces a major revision. Illness, migration, parenthood, loss, failure, recovery, or unexpected success can make an old identity impossible to maintain. The mind then faces a difficult task: preserving enough continuity to remain recognizable while changing enough to fit new reality. This is why major transitions can feel disorienting even when they are desired. The previous story explained your place in the world. When it stops working, the self may temporarily feel uncertain, not because a soul has disappeared, but because the organizing account has lost its structure. Over time, new habits, relationships, and interpretations can produce another version. The past is not erased. It is reassigned a new meaning. A failure becomes preparation. A wound becomes caution. A former ambition becomes a stage that once made sense. Still, calling the self a story does not mean that you are fictional or infinitely free to invent yourself. The body imposes needs and limitations. Temperament, development, culture, economic conditions, trauma, and relationships constrain which stories are possible. You cannot simply narrate away pain or declare a new identity without living through the changes that support it. A useful self-story must remain connected to evidence, action, and consequence. But it does mean that identity is not only something discovered. It is also something interpreted, practiced, negotiated, and revised. There may be no final sentence that defines you for all situations and all time. The person you call I may be the mind's best current explanation for a moving collection of tendencies, commitments, bodily states, relationships, and choices. That explanation can be incomplete without being meaningless. It can change without making every earlier version false. You are not a finished character reading from a script written at birth. You are the story, the storyteller, and the evidence that keeps forcing the story to change. And perhaps the deepest freedom does not come from finding one permanent self hidden beneath every role, but from recognizing that the narrative is still being updated, and that each honest action gives the next version of you something more truthful to become. Why some stars you see may no longer exist. A point of light can remain visible long after the object that produced it has changed beyond recognition. Yet the popular claim that most stars in the night sky are already dead is almost certainly false. The truth is more precise, and in some ways more interesting. Stars do not all live for the same amount of time. Their lifetimes depend mainly on mass. Small stars consume their nuclear fuel slowly and can survive for tens or even hundreds of billions of years. Stars similar to the Sun remain active for roughly 10 billion years. Very massive stars live much faster, burning through their fuel in only a few million years before collapsing, exploding, or shedding their outer layers. This means a star's distance alone does not tell you whether it still exists. You must compare how long its light has been traveling with how long that kind of star is expected to live. Most stars visible to the unaided eye are within a few hundred or a few thousand light years of Earth. Their light is old by human standards, but often very young compared with stellar lifetimes. A stable star that normally survives for billions of years is unlikely to have disappeared during the few centuries between emitting the light you see and the present day. The situation becomes more uncertain for exceptionally massive stars because their lives are short enough for meaningful change to occur across astronomical travel times. Betelgeuse, the red supergiant in Orion, is a famous example. It lies hundreds of light years away and is approaching the final stages of stellar evolution. It will probably explode as a supernova at some point in astronomical terms, but scientists cannot say whether that has already happened. It may remain unchanged for many thousands of years, or the explosion may have occurred, and its light may still be traveling toward us. Both possibilities are consistent with what we currently know, and claiming that Betelgeuse is definitely already dead would be dishonest. The same caution applies to other distant massive stars. Their present condition cannot be known until new information arrives. When such a star reaches the end of its life, it does not simply switch off like a lamp. The core may collapse in seconds, while the outer layers explode into space at enormous speed. For days or weeks, the supernova can outshine an entire galaxy. Later, the expanding debris forms a glowing remnant enriched with elements produced during the star's life and explosion. At the center, the collapsed core may become a neutron star, or, if massive enough, a black hole. So when a star no longer exists, the phrase usually means it no longer exists in its previous form. Its matter and energy remain, redistributed into gas, radiation, a compact remnant, and new elements that may eventually enter later generations of stars and planets. Some of the most useful evidence about vanished stars comes from these remains. The Crab Nebula is the debris of a stellar explosion whose light reached Earth in the year 1054. Historical observers recorded a brilliant new object in the sky, bright enough to be seen during the day. Today, the original star is gone as an ordinary star, but its collapsed core survives as a rapidly spinning neutron star. The surrounding nebula continues expanding, carrying a visible record of the event. In other cases, astronomers can detect a star shortly before it disappears. Modern telescopes repeatedly photograph nearby galaxies, sometimes capturing massive stars years before they explode. When a supernova later appears at the same position, researchers can compare the earlier images and identify the likely progenitor. A star that once existed as a luminous point can vanish from later observations, leaving behind an expanding cloud and perhaps an invisible compact object. There are even cases in which a massive star appears to fade without producing the bright supernova expected, raising the possibility that some stars may collapse more directly into black holes. These candidates remain difficult to confirm, but they remind scientists that stellar death can follow more than one path. The stars you see also belong to different stages of evolution. Some are young, hot stars burning hydrogen rapidly. Others are swollen giants that have exhausted fuel in their cores and begun fusing heavier elements in surrounding layers. Some bright objects that look like single stars are actually binary systems whose members exchange matter, altering their lifetimes and final outcomes. A massive star can strip material from a companion or lose its own outer layers, changing the kind of explosion it may eventually produce. This is why astronomers cannot determine a star's fate by brightness alone. They study its spectrum, temperature, chemical composition, pulsations, mass, and movement to understand what stage it has reached. Even then, stellar evolution contains uncertainties, especially near the final years of massive stars. The most important correction is therefore one of scale. A star being distant does not automatically make it dead, and an old-looking star is not necessarily near its end. Red dwarfs, the most common type of star in the galaxy, burn so slowly that none should yet have died from old age, because the universe itself is not old enough. The sun will not suddenly vanish after its light leaves. It will change gradually over billions of years, eventually becoming a red giant and later a white dwarf. Massive stars are different, living short and violent lives, but they are rare. The night sky is therefore not a cemetery filled mostly with extinguished suns. It is a mixed population of stars, whose visible light tells us what condition they occupied when that light departed. Some are almost certainly still shining much as we see them. Some have changed slightly. A small number may already have ended their stellar lives, while the news of that ending remains on its way. This uncertainty is not a flaw in astronomy. It is the unavoidable cost of receiving information across distance. A star does not become unreal when it changes before you learn about it. For a while, two truths coexist in different places: the star's actual present condition, whatever it may be, and the older state still crossing space toward your eyes. Somewhere, a massive star may already have collapsed, its core compressed, its outer layers racing outward, while Earth continues to receive the calm light it emitted before disaster began. You can look at that light tonight and see a star that may no longer exist in the form shown to you, not because the sky is lying, but because the universe delivers every distant ending only when its final signal arrives. How consciousness makes the universe feel personal. The universe contains no label with your name on it, yet consciousness makes certain sounds, faces, places, and events feel as though they belong uniquely to you. A storm does not know whose home it approaches. A star does not shine more brightly because someone loves it. And time does not slow because a farewell feels unbearable. Physical events unfold without consulting personal meaning. But the moment they enter conscious life, they are divided into what matters, what threatens, what comforts, what belongs, and what can be ignored. This is how an impersonal universe becomes the world of your experience. Consciousness does not merely register that something exists. It places that thing in relation to a body, a history, a goal, and a point of view. A sound across a crowded room may disappear into background noise until it forms your name. Then attention turns almost automatically. Psychologists often connect this familiar effect to selective attention. The brain continues processing more information than consciousness can fully contain, while signals with strong personal relevance gain priority. Your name is not physically louder than the surrounding conversation, but years of association have made it unusually important to the systems deciding what deserves awareness. The same principle applies to the face of someone you love, the sound of a crying child, the street where you once lived, or a message from a person whose opinion matters to you. The universe offers events, consciousness ranks them. This ranking is not an optional decoration added after neutral perception. It helps determine what you notice, what you remember, and how you act. The brain contains interacting networks involved in attention, emotion, memory, and decision-making. Among them, regions often grouped into the salience network help detect events that may require a shift in attention or behavior. A sudden noise, an unexpected expression, a bodily warning, or an emotionally significant thought can interrupt whatever you were doing and pull awareness toward itself. Salience is not a fixed property contained entirely within an object. A knife on a kitchen counter may be ordinary to a cook, threatening during an argument, and emotionally painful to someone reminded of an accident. Its physical shape remains unchanged while its place in conscious reality transforms. The meaning comes from a relationship between the object and the organism encountering it. This is one reason two people can stand in the same location and inhabit profoundly different personal worlds without either person inventing the environment. One sees a childhood home, another sees an old building, one hears a song, another hears the final evening of a lost relationship. Consciousness binds present information to private significance, allowing physical surroundings to carry layers that no instrument could measure by examining the objects alone. The room contains furniture, light, air, and sound, but the experienced room may also contain safety, shame, anticipation, or grief. These qualities are real as experiences, even though they are not independent substances floating between the walls. A photograph can record the visible arrangement, but it cannot capture what the arrangement means to the person looking at it. Personal reality also depends on the way the brain organizes space around the body. Neuroscience distinguishes between distant space and peripersonal space, the region immediately surrounding the body where objects can be reached, avoided, or used. Neurons in several brain areas respond to combinations of visual, auditory, and touch-related information near particular parts of the body. An object moving toward your hand or face can therefore acquire urgency before contact occurs. The space around you is not represented as empty geometry alone. It is mapped according to possible interaction. A distant branch may be scenery, but the same branch moving toward your eye becomes an immediate event. Consciousness makes the universe personal partly by organizing it around what can happen to you and what you can do next. Near and far, safe and dangerous, reachable and unreachable are not merely descriptions of distance, they are action-centered meanings. This body-centered organization creates an experienced world that seems naturally arranged around your position, even though the physical universe has no privileged viewpoint. Wherever you move, your perspective moves with you. The scene is continually reorganized into what lies ahead, behind, above, below, within reach or outside control. This does not mean you believe yourself to be the center of the cosmos. It means every conscious life must begin from somewhere. You cannot see from all positions at once, feel every body, or pursue every possible goal. Experience arrives from one location and is evaluated through one limited set of needs. The universe becomes personal because consciousness is situated. It belongs to a living system that can be helped or harmed, satisfied or frustrated, connected or abandoned. Emotion intensifies this transformation by giving experience what researchers call valence, the quality of feeling positive, negative, attractive, unpleasant, or urgent. Without valence, events might be recognized without carrying the same force. Damage to certain brain systems can leave a person capable of describing a situation while reducing the emotional weight that would normally guide a choice. The facts remain available, but they no longer feel equally important. This shows that knowing something and caring about it are partly separable. Consciousness feels personal because information is not only represented, it is valued. Food matters differently when you are hungry. A risk feels different when someone you love is exposed to it. A future reward can motivate years of effort because the mind gives a possible event emotional weight before it exists. The universe itself contains no universal scale declaring one outcome meaningful and another empty. Living minds create local systems of value based on survival, attachment, learning, culture, and individual history. This value is not limitless or entirely chosen. It is shaped by biology and experience, often before conscious reasoning begins. Reward-related circuits can increase the pull of certain goals. Fear learning can make a harmless cue feel dangerous long after the original threat has disappeared. Social rejection can activate some of the same broader networks involved in distress, because belonging has been deeply important throughout human evolution. A sentence spoken casually by one person may remain inside another person for years because it became attached to identity, hope, or humiliation. Physical energy produced the sound, but consciousness gave it duration far beyond the vibration itself. The event ended in the room. Its personal reality continued in memory, expectation, and behavior. The sense of agency makes the world even more intimate. You do not experience all movement as equivalent. A cup sliding because you pushed it feels different from a cup moving unexpectedly. The brain compares intended actions with their predicted consequences, helping generate the feeling that I caused this. When the match is strong, the result can feel like an extension of your will into the environment. A thought becomes a movement, the movement changes an object, and the object's change confirms your presence as an actor. This sense of agency can be disrupted in certain neurological and psychiatric conditions, revealing that the feeling of authorship is a constructed achievement rather than a simple fact automatically attached to movement. Normally, however, it allows the world to divide into what happened to you, what happened around you, and what happened because of you. These distinctions are central to responsibility, control, regret, and pride. A tree falling in the distance may be an observed event. A tree planted by your own hands becomes part of a personal history because your action is woven into its existence. Consciousness connects cause with ownership and turns neutral change into achievement or consequence. Another important process is the self-reference effect. Information connected to oneself is often remembered better than information processed in less personally relevant ways. When people judge whether a trait describes them, for example, they frequently recall that trait more effectively later than when they merely examine its spelling or general meaning. Self-related processing gives information additional routes into memory because it links new material with a rich network of existing associations. This does not mean the mind stores everything involving the self accurately. Personal memories can be distorted, selective, or reconstructed, but it helps explain why events tied to your own life feel denser than events of equal physical scale happening to strangers. Thousands of people may walk through an airport, yet the gate where you said goodbye can become more psychologically significant than the rest of the building combined. One location becomes heavy with meaning because consciousness has connected it to a private network of emotion and memory. Language deepens this personalization by allowing experience to be named, shared, and placed inside larger human meanings. A collection of rocks becomes a border, a monument, a grave, or a home depending on the concepts and histories attached to it. An astronomical object can become a navigational guide, a deity, a scientific target, or a reminder of someone who once watched it beside you. Language does not manufacture the physical object, but it changes how consciousness can relate to it. Once something is named, it can be discussed when absent, compared with distant events, and preserved across generations. Why the laws of physics might not be the final layer. The laws of physics may feel like the deepest rules reality can possess, yet some of them may be closer to the behavior of a surface than to the machinery hidden beneath it. When you watch waves move across water, you can describe their speed, shape, interference, and collapse without tracking every molecule in the ocean. The rules of the waves are real, measurable, and predictive, but they are not the most fundamental description of what the water is doing. They emerge from the collective behavior of countless molecules obeying another level of physics. Temperature offers a similar lesson. A single atom does not possess temperature in the ordinary sense. Temperature becomes meaningful when many particles move and exchange energy together. Pressure, fluid flow, elasticity, and even the solidity of ordinary materials arise from large numbers of microscopic interactions. These examples show that a law can be completely valid at one level, while emerging from structures at another. Some physicists suspect that the deepest laws currently known may work in the same way. They may describe the stable patterns visible at the scale of particles, fields, planets, and galaxies, without revealing the more basic system from which those patterns arise. Modern physics rests mainly on two extraordinarily successful frameworks. General relativity describes gravity as the geometry of space-time and explains the motion of planets, the evolution of stars, gravitational waves, and the large-scale structure of the cosmos. Quantum theory describes matter and the non-gravitational forces with remarkable precision. Its most developed particle physics form, the Standard Model, accounts for electrons, quarks, photons, neutrinos, and the interactions that govern atoms. Both frameworks have survived demanding experimental tests, yet they do not fit together completely. General relativity treats space-time as a smooth geometric structure, while quantum theory describes physical systems through probabilities, uncertainty, and fields that can fluctuate. In ordinary situations, the disagreement remains hidden because gravity is weak at microscopic scales and quantum effects are small across astronomical distances. But in places where extreme gravity and tiny scales meet, such as the earliest moments of cosmic history or the deepest regions associated with black holes, the two descriptions cannot both be used without difficulty. Calculations can produce infinities that do not correspond to meaningful predictions, signaling that at least one framework is incomplete in those conditions. This does not mean either theory is wrong in the domains where it has been tested. Newton's laws did not become useless when relativity was developed. They became recognized as an excellent approximation for objects moving slowly in weak gravity. In the same way, relativity and quantum field theory may one day be understood as powerful limits of a deeper structure. One important clue comes from the idea of effective theories. Physicists often build a theory to describe a particular range of distances and energies without claiming that it remains fundamental at every possible scale. A low-energy theory can ignore details that become important only under extreme conditions. This is not carelessness. It is one of the reasons physics can make accurate predictions without first solving the entire universe. To predict the motion of a bridge, an engineer does not need to calculate the behavior of every quark inside the steel. The microscopic details combine into stable properties, such as strength and elasticity. At another level, chemistry can explain reactions without separately solving every part of quantum field theory. Each layer has its own useful concepts, and those concepts may disappear when the scale changes. A sound wave is meaningful in air, but if you zoom down to the level of isolated molecules, the wave is no longer a separate object. It is a pattern distributed across their motion. Particles themselves might someday be understood in a similar way, not as the final pieces of reality, but as excitations, defects, vibrations, or stable patterns arising from something deeper. This possibility is already partly present in known physics. What we call a particle is described as an excitation of a quantum field, not simply as a miniature hard object. But quantum fields may not be the final layer either. Some approaches to quantum gravity propose that space-time and particles emerge together from more fundamental relationships. String theory explores the idea that apparently different particles could arise from different vibrational states of more basic extended objects. Loop quantum gravity investigates whether spatial geometry may possess a discrete quantum structure rather than remaining smooth at every scale. Other research programs examine whether space-time could emerge from quantum information, networks of relationships, causal connections, or patterns of entanglement. None of these proposals has yet been confirmed as the final theory, and it would be misleading to speak as though physicists have already discovered what lies beneath space-time. Their importance comes from showing that the foundations of physics are still open questions. Even space, time, and particles, concepts that seem necessary for describing anything, may turn out to be products of a deeper order rather than the starting ingredients. The apparent laws of nature can also change their expression with scale. The strengths of particle interactions are not fixed in exactly the same way at every energy. Quantum effects cause measured interaction strengths to vary as experiments probe shorter distances or higher energies. At ordinary scales, the electromagnetic, weak and strong forces appear distinct. At higher energies, some of their strengths move closer together, encouraging the idea that forces which now seem separate may once have been aspects of a more unified interaction. The electromagnetic and weak forces have already been successfully described as two manifestations of a single electroweak framework. In the early universe, when temperatures were extremely high, the distinction between them did not exist in the form observed today. As the universe cooled, the state of the fields changed, and the forces acquired their present differences. This is similar, in a limited sense, to how the same material can behave as liquid water or solid ice depending on conditions. The underlying system remains, but the visible rules and symmetries change with the state it occupies. If some laws depend on the condition of the universe, then what appears timeless and universal to us may partly reflect the physical phase in which we happen to exist. This possibility becomes especially significant when physicists ask why the constants of nature have the values they do. The masses of particles, the strengths of forces, and other parameters are measured extremely precisely. But the standard model does not explain all of them from deeper necessity. It accepts many as inputs determined by observation. A more fundamental theory might eventually derive those values, showing that they could not have been otherwise. But another possibility is that some values depend on the state of underlying fields or on which stable region of a wider physical structure developed. Ideas involving multiple possible vacuum states, cosmic inflation, or a broader landscape of solutions explore this possibility, although they remain uncertain and difficult to test. The existence of unexplained constants does not prove that the laws are accidental, but it reveals that present theory does not yet tell us why nature chose its particular settings. There is also the question of why physical laws are so widely uniform. Experiments indicate that the same basic rules apply across the observable cosmos. Light from distant galaxies shows atomic signatures consistent with the same elements and quantum transitions measured on Earth. This uniformity allows science to reconstruct cosmic events, but the laws themselves do not explain why they possess this reach. Are they fixed principles existing independently of the universe, mathematical necessities that could not be different, habits established by cosmic history, or regularities emerging from a deeper system? Physics can describe what the laws do far better than it can explain what a law ultimately is. The word law can create a misleading image of commands imposed upon matter, as though the universe were reading instructions and obeying them. In practice, a physical law is a compact description of regularities observed in nature. Gravity does not consult an equation before a planet moves. The equation is a human representation of the pattern. This raises a difficult question. Are the equations uncovering rules built into reality? Or are they identifying stable relationships that emerge because the universe is organized in a certain way? The distinction may seem philosophical, but it affects what physicists search for. A final theory might be expected to provide one unique mathematical structure from which every particle and force follows. An emergent view might instead suggest that the laws are like the rules of a crystal, a fluid, or a biological system, robust at the level where they appear, yet dependent on deeper constituents and historical conditions. Emergence does not make a law less real. A hurricane is not unreal because it consists of moving air and water. A living cell is not unreal because it is made from molecules. The higher level pattern can possess behaviors that are difficult to predict by staring only at the components. Physicists use the word universality for a related phenomenon. Very different microscopic systems can display the same large-scale behavior under certain conditions. Why reality becomes stranger at the smallest scales. Shrink far enough below the world of tables, stones, and living bodies, and reality stops behaving like a collection of miniature objects with fixed positions, and begins to resemble a set of possibilities governed by rules that have no comfortable equivalent in everyday life. An atom is not a tiny solar system with electrons circling a nucleus along neat tracks. Electrons are described by quantum states that tell us the probabilities of where certain measurements may find them and how they can interact. Before a measurement, asking for one exact hidden path may not merely be difficult. In many situations, the theory does not assign such a path at all. This is one reason the smallest scales feel so strange. Human intuition was shaped by large objects whose quantum behavior has been averaged across enormous numbers of particles. A ball appears to possess a clear location because interactions with light, air, heat, and its surroundings constantly destroy any delicate quantum alternatives before they can become noticeable. At microscopic scales, those alternatives can survive long enough to affect experiments. A particle can be prepared in a state containing several possible outcomes, and those possibilities can interfere with one another like overlapping waves. The result is not that the particle is secretly jumping between ordinary locations too quickly to see. Quantum interference produces patterns that cannot be explained by assigning it one classical history from the beginning. Yet when an interaction forces a definite result to be recorded, only one outcome appears. Scientists can predict the probabilities with extraordinary accuracy, but the individual result is not generally determined in the same way as the path of a thrown stone. Nature seems to offer reliable statistics without always offering a predictable answer for each single event. This does not mean that anything can happen. Quantum possibilities are tightly constrained by the physical state, conservation laws, and the structure of the experiment. The strangeness is disciplined, not chaotic. Another departure from ordinary experience is quantum tunneling. A classical object without enough energy to cross a barrier must remain trapped. But a quantum particle can sometimes be detected on the other side. It does not need to smash a hole through the barrier or secretly borrow energy in the popular sense. Its quantum state can extend into and beyond a region that classical physics would forbid, giving a small but real probability of transmission. This process helps make radioactive decay possible, contributes to nuclear fusion in stars, and is used in technologies such as scanning tunneling microscopes, which can reveal surfaces at the scale of individual atoms. At small scales, even identical particles challenge the idea of separate identity. Every electron has the same basic properties as every other electron. There is no hidden label engraved upon one that allows nature to distinguish it from another. When identical quantum particles exchange places, the system may remain physically unchanged, and this indistinguishability produces powerful collective rules. Electrons belong to a family of particles that cannot all occupy the same quantum state within an atom. This exclusion is why electrons fill different atomic energy levels, and why matter develops the chemical structure required for complex materials. Other particles, such as photons, behave differently and can gather into the same state, helping produce phenomena such as laser light. The large world around you therefore depends on microscopic entities that do not preserve individuality in the familiar human sense. Quantum uncertainty adds another limit. Some properties cannot simultaneously possess arbitrarily precise values in the same state. The more sharply a particle's position is defined, the less sharply its momentum can be defined. And this is not simply because an instrument is clumsy. The uncertainty belongs to the quantum description itself. A tightly confined particle must involve a wider range of possible momenta, much as a sharply localized wave requires many different wavelengths to build it. This prevents electrons from collapsing quietly into atomic nuclei and helps determine the size and stability of atoms. The uncertainty principle is not a statement that nothing can be known. It tells scientists exactly how certain kinds of precision are related, and experiments confirm those limits. Even measurement has a different meaning here. Measuring a microscopic system requires a physical interaction between the system and an apparatus. The apparatus becomes correlated with the property being measured, and the result is amplified into a stable record, a spot on a detector, a current in a circuit, or a number stored in a computer. Consciousness is not required to make the particle behave quantum mechanically. The essential process is interaction and the creation of a record that can no longer maintain all alternatives coherently. This connection to the environment is called decoherence. It explains much of why large objects do not visibly occupy fragile combinations of distinct states. Countless surrounding particles continually interact with them, spreading quantum information into the environment so rapidly that interference between large-scale alternatives becomes effectively impossible to observe. Decoherence does not by itself settle every philosophical question about why one particular outcome is experienced, but it explains how the strange quantum world gives rise to the stable classical world you recognize. There is no precise border where quantum rules suddenly switch off. The chair beside you, the air in the room, and your own body are all quantum systems at the microscopic level. Their ordinary behavior emerges because they contain enormous numbers of components interacting with one another and with their surroundings. The familiar world is therefore not separate from quantum reality. It is what quantum reality looks like after delicate possibilities have been averaged, entangled with the environment, and organized into durable patterns. Experiments increasingly place larger molecules and engineered devices into states that display quantum interference, showing that strangeness is not restricted to one special class of tiny object. The practical limit is maintaining isolation and control, which becomes harder as a system grows. This leads to a deeper lesson. Reality does not become strange at small scales because nature abandons reason. It becomes strange because the rules that feel obvious to you, fixed paths, separate identities, definite properties, and barriers that cannot be crossed, are not the deepest rules. They are large-scale habits that emerge when quantum systems become complex and exposed to their surroundings. Beneath those habits lies a world of probability amplitudes, interference, tunneling, indistinguishable particles, and measurable limits on what can be definite at once. These ideas resist ordinary pictures, yet they produce some of the most accurate predictions ever made. The smallest scales do not reveal a universe without order. They reveal an order so different from daily experience that intuition must step aside and let experiment lead. And perhaps that is why the quantum world feels less like a smaller version of reality, and more like the hidden grammar from which familiar reality is slowly written. How the mind searches for meaning in a silent cosmos. The cosmos has never answered a human question in words, yet the human mind continues to ask as though silence itself must contain a reply. You look at a night sky that offers no visible instructions, no explanation of why you were born, no promise that suffering will be balanced, and no sign that the universe has arranged its history around your existence. Still, the mind resists leaving events unconnected. It searches for patterns, causes, intentions, and stories, because a world that can be interpreted is easier to navigate than one that feels random. This tendency begins with survival, an organism that quickly notices a repeated sound near danger, recognizes the tracks of a predator, or connects a certain plant with illness, gains an advantage. The brain therefore became highly sensitive to regularity. It does not wait passively for perfect evidence. It forms expectations from incomplete information and updates them when events do not fit. Most of the time, this ability is useful. It allows you to learn language, predict other people, recognize familiar places, and prepare for what may happen next. But the same system can discover patterns where none were intentionally placed. This is called apophenia, the tendency to perceive meaningful connections in unrelated or random events. A sequence of coincidences may feel planned. A vague shape becomes a face. An ordinary setback appears to be part of a larger message. The pattern can feel emotionally powerful because the brain does not experience meaning as a cold conclusion. Meaning influences attention, memory, motivation, and the sense of control. Once a possible connection is noticed, confirming details become easier to remember, while contradictions may fade into the background. This is one reason people can become convinced that unrelated events are secretly linked, even when careful testing finds no reliable pattern. Yet not every search for meaning is an error. Human beings also create genuine meaning by connecting experiences to values, goals, and relationships. The universe may not assign a purpose to an action, but a mind can understand why that action matters within a life. Caring for someone, completing difficult work, protecting a community, or learning about nature can become meaningful because these activities organize attention and effort around something considered valuable. Psychology often distinguishes between meaning as coherence, purpose, and significance. Coherence is the feeling that life makes enough sense to be understood. Purpose is the sense that present actions are moving toward a future goal. Significance is the belief that one's existence matters in some wider context, even if that context is only a family, a group, a tradition, or the lives one influences. These forms of meaning do not require the cosmos to possess human intentions. They can arise from the way conscious beings relate to one another and to the conditions of their lives. The search becomes especially intense when ordinary explanations collapse. Loss, illness, disaster, rejection, and sudden change can break the story a person used to understand the world. Psychologists sometimes describe the resulting struggle as a conflict between global meaning, the broad beliefs a person holds about fairness, identity, control, and purpose, and the meaning of a specific event. If someone believes that careful behavior always prevents harm, an unpredictable tragedy can shatter more than a plan. It can damage the structure through which life previously made sense. The mind then tries to repair the conflict. It may revise beliefs, change goals, search for causes, or place the event inside a new narrative. This process can lead to growth, but growth is not guaranteed, and suffering should not be romanticized as secretly necessary. Some events remain painful without offering a hidden lesson. Meaning-making is not proof that the event was designed for a purpose. It is the mind's attempt to continue living after the old explanation no longer works. The awareness of mortality adds another pressure. Humans can understand that their lives will end and that the universe will continue without them. Research associated with terror management theory suggests that reminders of death can strengthen attachment to cultural beliefs, identities, and groups that offer a sense of continuity or value. People may defend their worldview more strongly when mortality becomes emotionally present, because a stable system of meaning can soften the fear of being temporary. Religion, philosophy, national identity, family traditions, creative work, and scientific discovery can all provide ways of placing one finite life inside something that appears larger and more lasting. These systems are not psychologically identical, and their truth cannot be decided merely by explaining why people find them comforting. A belief can be comforting and true, comforting and false, disturbing and true, or disturbing and false. Psychology can study why a mind seeks meaning, but it cannot settle every philosophical or religious claim about whether an ultimate meaning exists. Science itself is one disciplined response to cosmic silence. Instead of assuming that events carry personal messages, it asks which patterns remain when observations are repeated, measurements are compared, and preferred explanations are exposed to the possibility of failure. This method does not remove wonder. It protects wonder from becoming whatever the observer wants to believe. The stars are not interpreted as warnings or rewards. Their light is examined for evidence of temperature, composition, motion, and history. The silence of the cosmos becomes a question that can be approached carefully. Searches for extraterrestrial intelligence, for example, do not begin from the certainty that someone is trying to contact us. They examine the sky for signals that differ from known natural processes and could survive independent testing. So far, no confirmed evidence of intelligent extraterrestrial communication has been found. The absence of such evidence does not prove that humanity is alone, but it prevents desire from being mistaken for discovery. This restraint is difficult because the mind prefers closure. An unanswered question creates tension, and a confident story can feel better than uncertainty, even when the evidence is weak. Learning to remain with uncertainty is therefore not the abandonment of meaning. It is a more honest form of meaning-making, one that allows mystery to remain mystery without filling every silence with invention. Awe may help with this balance. Studies of awe suggest that encounters with vast natural scenes, art, music, or powerful ideas can reduce the immediate dominance of the self and increase the feeling of belonging to something larger. Standing beneath a dark sky can make personal concerns feel smaller without making them worthless. The scale of the cosmos may not give you a purpose, but it can change the scale at which you examine your problems. It can remind you that the mind capable of feeling insignificant is also capable of understanding distances, histories, and processes far beyond the needs for which it originally evolved. This does not prove that consciousness occupies a privileged place in nature. It shows that matter organized into a human brain can ask what matters. Notice that the universe does not answer automatically and still choose how to respond. The silence becomes most frightening when it is interpreted as evidence that nothing matters. But this conclusion does not logically follow. The absence of an externally announced purpose does not erase pain, joy, responsibility, or consequence. A promise matters because another person can be harmed when it is broken. Kindness matters because conscious creatures can suffer and recover. Knowledge matters because better understanding changes decisions. A life does not need to alter a galaxy in order to alter the experience of someone living within it. Meaning can be local without being false, just as warmth can be temporary without being imaginary. The mind's danger lies in turning every coincidence into a cosmic plan. Its strength lies in creating values that remain accountable to reality. You can admit that the universe may be indifferent while refusing to become indifferent yourself. You can search for evidence without demanding that evidence flatter you. You can build purpose without pretending it was written into the stars before you arrived. Perhaps the cosmos is silent because silence is simply what a universe without a human voice sounds like. And perhaps the task of the mind is not to force that silence into an answer, but to listen carefully enough to separate what has been discovered from what has been hoped, then choose what kind of meaning can be lived honestly beneath a sky that promises nothing and still leaves you free to care. Why the universe might be mostly invisible. The most misleading thing about the universe may be that the part which shines is the part you are least likely to mistake for the whole. When you look through a telescope, the cosmos appears crowded with stars, glowing nebulae, bright galaxies, and violent explosions. So it is natural to think that light reveals most of what is there. Yet the luminous universe is only a thin visible surface laid over a far larger hidden inventory. According to the standard cosmological model, ordinary atomic matter, the material that forms stars, planets, oceans, bodies, and every object you have ever touched, accounts for only about 5% of the total matter and energy content of the cosmos. Dark matter contributes roughly 27%, while the remaining 68% is assigned to the still unexplained phenomenon called dark energy. These percentages are model-based estimates rather than a direct sorting of the universe into containers, but they fit a wide range of observations with remarkable success. Even the familiar 5% is far less visible than its name suggests. Most ordinary matter is not gathered into stars, worlds, or living organisms. Much of it exists as diffuse hydrogen and helium gas, often spread so thinly between galaxies that it produces almost no visible glow. Some of this gas lies in the long filaments connecting groups and clusters, heated to temperatures at which its atoms lose electrons and become difficult to detect. For years, astronomers knew from measurements of the early universe how much ordinary matter should exist, yet inventories of nearby stars, galaxies, and easily observed gas could not account for all of it. A significant portion of these once missing baryons is now understood to occupy the warm-hot intergalactic medium, an extremely faint web of gas traced through subtle absorption, X-ray signals, and its effects on background radiation. This means that even the matter made from familiar atoms can remain hidden not because it is exotic, but because it is too cold, too hot, too sparse, or too weakly luminous for ordinary sight. The stars that dominate astronomical photographs are therefore not a fair sample of cosmic matter. They are the small fraction that has become dense and hot enough to announce itself. A galaxy may look like a bright island, but most of its volume contains darkness, thin gas, compact remnants, dust, and an unseen gravitational structure extending far beyond the visible stars. That larger structure is what astronomers call a dark matter halo. Dark matter is not described as dark merely because it is difficult to illuminate. Available evidence indicates that it does not emit, reflect, or absorb electromagnetic radiation in the ordinary way, which means no conventional telescope can photograph it directly. Scientists infer its presence from gravity. Stars in the outer regions of galaxies orbit faster than the visible matter alone appears able to explain. Galaxies inside clusters move as though they are held by far more mass than can be found in their stars and hot gas. Light from more distant objects is bent and distorted when it passes through foreground concentrations of mass, allowing astronomers to map gravitational structures that produce little or no light. These effects do not reveal what dark matter is made from, but they show where its gravity acts. You can think of it as seeing footprints without seeing the walker, although the analogy should not suggest that scientists possess only one isolated clue. Galaxy motion, gravitational lensing, the growth of large-scale structure, and patterns in ancient cosmic radiation all point toward an additional form of gravitating matter. Without it, galaxies like the Milky Way would not have developed in the same way, and simulations struggle to reproduce the vast network of filaments and clusters observed across the cosmos. Dark matter appears to have gathered first, forming gravitational wells into which ordinary gas later fell. The visible universe may therefore resemble lights strung along an invisible framework. The stars reveal where ordinary matter became concentrated, while the underlying architecture is dominated by something that has never been collected in a laboratory or identified as a confirmed new particle. Many candidates have been proposed, including weakly interacting particles, axions, and other forms of matter beyond the established particle model. Experiments have been built deep underground, in space, and inside powerful colliders to search for direct evidence, but no candidate has yet been conclusively detected. Scientists also test whether some observations attributed to dark matter could instead point to an incomplete theory of gravity. Such alternatives must explain not one galaxy, but the full collection of evidence, from galaxy clusters to the early universe. So far, dark matter remains the leading framework, but its identity remains unknown. This distinction matters. There is strong evidence for an unseen gravitational component, but there is no confirmed answer to what that component physically is. Dark energy is hidden in a different way. It does not gather around galaxies like dark matter, and it should not be pictured as a black fluid flowing through space. The term is a name for whatever accounts for the observed acceleration of cosmic expansion. Astronomers discovered this acceleration by comparing the apparent brightness and distance of exploding stars, then strengthened the evidence using measurements of galaxy clustering, ancient radiation, and the expansion history of the cosmos. In the simplest successful model, dark energy behaves like a constant property of space, whose density does not thin out as the universe grows. But this description may be incomplete. Results from the Dark Energy Spectroscopic Instrument, based on its first 3 years of observations, have strengthened hints that dark energy might change over cosmic time. Although the evidence is not yet conclusive and requires further analysis, if those hints survive, the largest component of the cosmic inventory may be more dynamic than the standard model assumes. If they disappear with better data, the constant model will remain extraordinarily successful, while the deeper nature of dark energy stays unexplained. In either case, calling it dark energy does not mean scientists have found a substance and learned its properties. The phrase marks an observed effect and an unanswered question. This is what makes the universe's invisibility so unusual. The hidden parts are not all hidden for the same reason. Diffuse ordinary gas is difficult to see because it is spread thinly and radiates weakly. Dark matter is inferred because it gravitates while apparently avoiding ordinary electromagnetic interaction. Dark energy is inferred not as a collection of concealed objects, but through the changing behavior of expansion across immense scales. Black holes are dark because light that crosses their horizons cannot return, yet surrounding matter and gravitational effects can reveal their presence. Cold planets may emit too little visible light to be noticed beside their stars. Rogue worlds may travel through interstellar space almost entirely unseen. Dead stars can fade into dim white dwarfs, neutron stars, or black holes. Dust can hide luminous regions while glowing at wavelengths your eyes cannot detect. Neutrinos pass through planets and bodies in vast numbers, while interacting so rarely that enormous detectors are needed to catch even a small fraction. The word invisible therefore covers many different physical situations. Things that emit the wrong kind of radiation, things too faint or diffuse to detect easily, things concealed by other matter, things that interact extremely weakly, and phenomena known only through what they cause. Human vision occupies an especially narrow window. The night sky appears dark to your eyes, yet instruments operating in radio, microwave, infrared, ultraviolet, X-ray, and gamma-ray wavelengths reveal different structures layered across the same directions. A cloud that looks like a black gap in visible light may glow in infrared. A quiet galaxy may possess an energetic X-ray source at its center. Cold hydrogen can announce itself through radio emission, while remaining invisible to ordinary sight. The universe does not contain a natural division between visible and invisible. That division reflects the receptors humans inherited. Astronomy expands the senses by converting inaccessible radiation into images, sounds, and data. But even this broader electromagnetic view cannot reveal something that does not meaningfully interact with light. That is why gravity has become one of the most important instruments for studying the hidden cosmos. Gravity responds to mass and energy whether they shine or not. By measuring motion, distortion, clustering, and expansion, astronomers can reconstruct the influence of entities they cannot place directly in an image. The maps they build are less like photographs and more like investigations. A stretched galaxy becomes evidence of unseen mass in front of it. A pattern of galaxy motion becomes evidence of a gravitational well. A change in expansion becomes evidence of a component whose nature remains unknown. The invisible universe is not accepted because darkness feels mysterious. It is inferred because visible objects repeatedly behave as though more exists than the visible inventory can provide. Still, it is important not to let the percentages create a false sense of completion. Saying that the cosmos contains roughly 5% ordinary matter, 27% dark matter, and 68% dark energy does not mean 95% has been explained. It means observations can be described by dividing the cosmic budget into components with certain broad effects. Why other minds may be the deepest mystery around you. The person sitting closest to you may be more inaccessible than the most distant galaxy, because no matter how familiar their face becomes, you can never enter the private experience unfolding behind it. You can hear someone describe pain, watch their hands tremble, notice hesitation in their voice, and recognize the signs of fear, yet the fear itself remains unavailable to you. You do not feel their exact sensation, see through their point of view, or know with absolute certainty what is present in their awareness. This is the problem of other minds. The fact that your own consciousness is known from the inside, while every other consciousness must be inferred from the outside. You know directly that you are having an experience because the experience is happening to you. With everyone else, you rely on behavior, language, facial expression, memory, and similarity. A person says they are tired, and you believe them because you know what tiredness feels like. Recognize the signals and understand that their body and brain resemble yours. The inference is reasonable and necessary, but it is still an inference. There is no instrument that can display another person's awareness in the same way a screen displays an image. Brain scans can reveal patterns associated with seeing, deciding, remembering, or feeling pain. But neural activity is not the experience itself. It is evidence that a physical process is occurring, not a doorway through which you can inhabit what that process feels like. This gap remains even in the closest relationships. Two people can share a room, a loss, a celebration, or a lifetime, and still experience the same event differently. One may remember the silence, another the smell of the air. One may feel relief while another feels guilt. Language allows private worlds to approach one another, but words compress experience. Saying, "I am afraid," does not transmit the shape, intensity, bodily tension, memories, and expectations contained within that fear. It offers a sign that another mind must interpret using its own history. Communication is therefore not the transfer of experience itself. It is the exchange of symbols from which each mind builds an approximation of the other. The brain is remarkably skilled at this approximation. Humans develop what psychologists call theory of mind, the ability to represent other people as beings with beliefs, desires, intentions, and knowledge that may differ from one's own. This ability becomes visible in childhood through false belief tasks. A young child may initially assume that another person knows what the child knows. Later, the child begins to understand that someone can hold a mistaken belief based on limited information. This is a major cognitive achievement. It allows deception, teaching, cooperation, empathy, storytelling, and complex social life. You can predict that a friend will search where they last left an object, even when you know the object has been moved. You can hide a surprise, recognize a misunderstanding, or explain why someone acted on information that was false. These abilities depend on brain systems involved in social reasoning, including regions near the junction of the temporal and parietal lobes and areas along the brain's midline. But these systems do not read minds in a literal sense. They generate models of what another person may know or want. Like all models, they can be accurate, incomplete, or deeply mistaken. You may interpret silence as anger when it is exhaustion, confidence as arrogance when it is nervousness, or kindness as affection when it is politeness. The mind fills gaps because social life rarely provides complete information. It constructs hidden causes from visible effects. This can create empathy, but it can also create projection. You may believe you understand another person while actually placing your own motives inside them. When someone behaves differently from what you would do, the difference may feel irrational only because you do not possess the experiences, fears, priorities, and assumptions organizing their choice. The deepest mystery is not simply that another mind is hidden. It is that the mind you imagine behind another face is partly built by your own. Empathy is often described as feeling what another person feels. But in most cases, you are not reproducing their experience exactly. You are generating a response within your own nervous system based on what you observe and what you have learned. If someone injures a hand, you may flinch. If they cry, you may feel distress. These reactions help social connection, yet they remain your reactions. The other person's pain may be sharper, duller, frightening, familiar, or emotionally numb in ways your response does not capture. Even highly empathic people can misunderstand, because emotional resonance is not the same as knowledge. Sometimes empathy becomes more accurate when imagination is restrained and curiosity takes its place. Instead of assuming, "I know how you feel," you ask, "Listen," and allow the possibility that their inner world does not match your model. The mystery of other minds becomes especially clear when outward behavior and inner experience come apart. A skilled actor can display grief without being personally bereaved. A person in pain may smile to avoid concern. Someone with a neurological condition may be unable to communicate while remaining aware of what happens around them. In certain cases of severe brain injury, researchers have used brain imaging to detect signs that a patient understood instructions despite showing little or no visible response. These findings remind us that the absence of ordinary behavior does not always prove the absence of awareness. The reverse question is equally unsettling. Could something behave intelligently without possessing any inner experience? Philosophers use the idea of a philosophical zombie to explore a being that acts exactly like a conscious person while feeling nothing inside. There is no evidence that such humans exist, and the concept is a thought experiment rather than a scientific discovery. But it exposes the difficulty of proving consciousness from behavior alone. The same challenge appears in debates about artificial intelligence. A system may produce fluent language, describe emotions, and respond as though it understands, yet outward performance by itself does not settle whether there is any subjective experience behind the words. At present, there is no accepted scientific test that can conclusively determine consciousness in every possible system. Researchers examine architecture, behavior, learning, integration, and responsiveness. But the final question remains open, because consciousness is the very thing that cannot be observed from the outside in its first-person form. Other animals deepen the problem further. Mammals, birds, and many other creatures show learning, memory, flexible behavior, pain responses, social bonds, and signs of planning. Scientific evidence strongly supports the view that consciousness is not uniquely human, but the character and extent of animal experience remain difficult to determine. An octopus has a nervous system organized very differently from yours, with much of its neural processing distributed through its arms. A bat navigates through echolocation. A dog's world is shaped heavily by smell. To ask what it is like to be such an animal is to confront the limits of human imagination. You can study behavior and neural structure, but your own senses and concepts may be unable to recreate the form of another species' awareness. The mystery is not merely whether they experience, it is how experience might be organized when the body, senses, and way of acting are radically different. This uncertainty has ethical consequences. You cannot wait for perfect access to another mind before deciding whether its suffering matters, because perfect access may be impossible in principle. Moral life, therefore, depends on cautious inference. When a being shows credible signs of pain, preference, fear, attachment, or awareness, the responsible response is often to take those signs seriously. This is why societies protect infants, patients who cannot speak, animals, and people whose communication differs from the majority. Certainty is not required for compassion. In fact, the inability to know another mind completely may be one reason compassion is necessary. You act with care because there may be an entire world of experience where you can see only a gesture. Trust also begins in this uncertainty. Every confession, promise, and expression of love asks you to accept something you cannot independently verify. You can evaluate consistency, history, and behavior, but you cannot inspect sincerity directly. Intimacy is not the removal of the boundary between minds. It is the decision to approach that boundary honestly, again and again, using language, attention, and shared time. The closest person in your life remains partly unknown, not because the relationship has failed, but because consciousness is private by its nature. No amount of closeness turns two viewpoints into one, and perhaps this hiddenness is not only a source of loneliness, it is also what makes another person genuinely other. If every thought were exposed, if every emotion were instantly available, curiosity, interpretation, trust, and voluntary disclosure would lose much of their meaning. A mind becomes precious partly because it contains depths that cannot be taken by force. You can be invited into its memories and fears, but never own them completely. The problem of other minds has no final solution that converts another person's experience into your own. Science can strengthen the evidence, philosophy can clarify the limits, and conversation can narrow misunderstanding, but the first-person world remains singular. How the multiverse could change what real means. Reality may be far less exclusive than it feels, because the universe you inhabit might be only one physically realized possibility among many. The word multiverse often brings to mind endless copies of Earth, alternate versions of your life, and universes where every decision produces another you. But science does not offer one single multiverse theory. It offers several different ideas that emerge from different areas of physics, and none has yet been confirmed by direct observation. Understanding the distinction matters, because the multiverse is not one established discovery waiting to be photographed. It is a family of proposals asking whether the reality available to us is only one part of a much larger structure. One version grows from cosmic inflation, the theory that the very early universe passed through a period of extremely rapid expansion. Inflation helps explain why distant regions of the cosmos appear so similar, and why the geometry of space is so close to flat. In some models, inflation does not end everywhere at once. It stops in certain regions, allowing universes like ours to form, while continuing elsewhere and producing additional regions, often described as bubble universes. These bubbles would not necessarily float through ordinary space like soap bubbles inside a room. Each could contain its own expanding space-time, separated from the others so completely that communication may be impossible. Another multiverse idea comes from quantum mechanics. In the many worlds interpretation, a quantum event with several possible outcomes does not collapse into only one result at the deepest level. Instead, all outcomes remain part of a larger quantum state, while observers become connected to different branches and experience only one result. This does not mean that conscious decisions magically create universes, nor does it imply that every fantasy exists somewhere. The branches would arise from quantum interactions according to strict physical rules. The interpretation is mathematically compatible with standard quantum mechanics, but whether its other branches should be regarded as independently real remains a matter of scientific and philosophical debate. A third possibility appears in some versions of string theory, where the underlying equations may permit an enormous number of stable configurations. Different configurations could produce different particle properties, force strengths, or vacuum states. If cosmic processes realized many of these possibilities in separate regions, the laws that seem fundamental in our universe might be local conditions rather than universal necessities. Gravity might behave differently elsewhere. Certain particles might never form. Stable atoms, long-lived stars, or chemistry capable of supporting life might be impossible in most regions. Our universe would then look unusually suitable for observers, not necessarily because it was designed for them, but because observers can arise only in places where conditions permit complexity. This reasoning is related to the anthropic principle, which in its cautious form says that any observer will naturally find themselves in a region compatible with their existence. It does not explain why the larger structure exists, and it should not be used as a convenient answer whenever physics lacks one, but it changes the type of question being asked. A constant of nature may have its observed value because a deeper theory forces it to be that way, or because many values occur across a wider reality and conscious beings appear only in a narrow range. These possibilities lead to very different meanings of explanation. In a single universe, scientists usually search for one necessary reason why the laws possess their particular form. In a multiverse, some features might resemble environmental facts. The distance between Earth and the Sun is not a fundamental constant written into all possible reality. It is one local condition among countless planetary arrangements. In the same way, the strengths of forces or masses of particles might someday turn out to be local characteristics of our cosmic region. That would not make the laws unreal. A local law can govern every event accessible to you while still failing to describe all that exists. The multiverse could therefore separate real from universal. Something would not need to occur everywhere to be physically real. Your universe might be one consistent domain within a broader structure whose other domains obey different effective rules. This challenges the instinct that reality must be one stage containing one complete set of laws. It suggests that reality could be layered. What is possible in the deepest theory? What is realized somewhere? What is observable from here? And what becomes part of your particular history? These layers are not interchangeable. A mathematically allowed universe is not automatically a physically existing universe. A physically existing region is not automatically observable. An observable possibility is not automatically confirmed. Much confusion about the multiverse begins when these categories are treated as the same. The most serious difficulty is testability. If other universes are permanently unable to exchange signals with ours, how could their existence be distinguished from an elegant story? Science normally advances by making predictions that could fail. Researchers have considered whether collisions between bubble universes might have left patterns in ancient cosmic radiation, whether inflationary models could produce observable statistical signatures, or whether a deeper theory might predict a distribution of physical constants. So far, no observation has provided decisive evidence for another universe. The multiverse may eventually become testable indirectly if a well-supported theory predicts it as an unavoidable consequence and also succeeds in new measurable ways. But even then, Debate would remain about whether indirect necessity is enough to establish the reality of inaccessible regions. Science already accepts many objects through effects rather than direct images, but those effects occur within our observable world. Other universes could be more difficult because they might leave no accessible trace at all. This creates an uncomfortable boundary between physics and metaphysics. A proposal can arise from serious equations and still reach beyond what experiments can currently decide. The honest position is neither to dismiss the multiverse as pure fantasy, nor to present it as a known fact. It is a possibility produced by attempts to understand inflation, quantum theory, and the range of solutions allowed by fundamental physics. Its value lies partly in how sharply it exposes assumptions hidden inside the word real. You normally call something real when it can affect you, be measured, or participate in a shared world. But a multiverse could contain regions that exist without ever interacting with your history. Would they be less real because no message could reach you? If many worlds is correct, would an outcome you never experienced possess the same reality as the branch containing your life? If another universe has no common space, shared time, or causal relationship with ours, does it belong to the same reality, or should reality be reserved for each disconnected domain separately? Physics may eventually clarify the structure, but language will still struggle to contain it. The multiverse also changes the emotional meaning of uniqueness. In one interpretation, countless cosmic regions might contain similar galaxies simply because an enormous reality repeats broad patterns. In more speculative discussions, an infinite universe with limited ways of arranging matter could even produce distant configurations resembling familiar people and worlds, though such conclusions depend on assumptions that are far from established. Many worlds is sometimes said to imply versions of you experiencing other outcomes, but these versions would not form a hidden community of interchangeable selves. Once branches separate through decoherence, they would not normally communicate, reunite, or allow you to move between them. Their existence would not undo the consequences within your branch. A choice would still shape the only history available to the person making it. The possibility that another outcome occurs elsewhere would not return lost time, erase suffering, or make responsibility meaningless here. Reality is not made less serious merely by becoming larger. A book does not lose the meaning of one chapter because other chapters exist. Yet the multiverse could weaken the belief that your visible world exhausts possibility. The laws and events surrounding you might be one realized arrangement, rather than the only arrangement nature could permit. That thought can feel destabilizing because human understanding searches for a single foundation, a final stage beneath which nothing remains. The multiverse replaces that clean picture with plurality. There may be no unique cosmic history, no single collection of constants, and perhaps no view from which all branches or regions can be gathered into one observable scene. Still, the idea does not allow anything whatsoever to count as real. Each scientific multiverse proposal has rules. Inflationary regions must emerge from specific cosmological dynamics. Quantum branches must follow the quantum state. String theory vacua must satisfy the deeper mathematical framework. The larger reality may contain more possibilities than your universe displays, but it would not be a lawless warehouse where every contradiction becomes true. The mystery is not that imagination can invent unlimited worlds. It is that the laws already used to describe this world may naturally point towards structures far beyond it. Whether those structures exist remains unanswered. Why there may be no final bottom to reality. Every time humanity has believed it had reached the smallest furniture of existence, nature has quietly revealed another question beneath the floor. Matter once appeared to be made from solid, indivisible atoms. Atoms later revealed internal structure. Atomic nuclei revealed protons and neutrons, and those particles revealed quarks whose interactions create much of the mass and behavior of ordinary matter. Today, the standard model describes quarks and leptons as elementary, meaning no smaller internal components have been experimentally confirmed. But elementary is a statement about the limits of present evidence. not a guarantee that reality has finally reached its last layer. The same theory is extraordinarily successful while remaining incomplete, since it does not provide a complete account of gravity or explain several major observations. The deeper possibility is that searching for the bottom of reality may be like searching for the lowest point in a circle. The question assumes a kind of structure that nature may not possess. You instinctively picture reality as a stack of containers. A chair is made of molecules. Molecules are made of atoms. Atoms contain smaller particles. And eventually there should be one final object that is made of nothing else. But this picture comes from everyday manufacturing, where complex things are assembled from simpler pieces. Fundamental physics does not require the universe to be constructed like a machine built from permanent microscopic bricks. What appears to be a thing at one scale can become a pattern at another. A wave in the ocean is real, but there is no special wave substance hidden between the water molecules. A whirlpool has a recognizable shape, duration, and effect, yet it is made from water continually entering and leaving the pattern. The whirlpool remains while its material changes. Reality may contain entities that exist in this organized way, not as ultimate objects, but as stable patterns produced through relationships. Even the particles currently called elementary are described through quantum fields, where what appears in a detector is an excitation of a wider physical system, rather than a tiny classical bead carrying an obvious inner surface. Asking what the field itself is made of may eventually reveal something deeper, but it may also repeat the assumption that every explanation must consist of smaller material pieces. Perhaps the next level would be made from relations, information, events, or structures for which the word "made" no longer has its ordinary meaning. Physics already uses effective theories that describe nature accurately within particular ranges of distance and energy, without claiming to reveal every deeper detail. A theory of fluids can predict waves and currents without following each molecule. Chemistry explains bonds and reactions without calculating every underlying field interaction separately. The lower level constrains the higher one, yet the higher level develops concepts that are not useful when looking only at its smallest constituents. Wetness is not found inside an isolated molecule, and biological metabolism is not a property of one atom. These features arise when components enter certain arrangements. The reverse may also be true. The laws seen at a microscopic level could themselves be the large-scale behavior of an unknown underlying system. Modern effective field theory methods are built around the recognition that physics at accessible energies can remain predictive even when deeper, higher energy processes are unknown. This creates an unsettling possibility. If each level hides details that do not matter to the level above, then evidence available at one scale may never uniquely identify what lies beneath it. Different microscopic systems can sometimes produce the same collective behavior. Ice, magnets, fluids, and other systems can display surprisingly similar mathematical patterns near certain transitions, even though their microscopic ingredients are different. The higher level pattern may forget much of the lower level construction. If fundamental physics works similarly, several different underlying realities might generate the same particles and forces we observe. Even perfect knowledge of our current layer might then fail to reveal one unique foundation. Reality could possess depth without leaving a clear staircase downward. The concept of size may also lose meaning before a final object is found. Physicists often discuss the Planck length, an extraordinarily small scale formed by combining constants associated with quantum theory, gravity, and light. Its value is about 1.5 times 10 to the power of -35 meters. It is frequently described in popular explanations as the smallest possible length or the pixel size of the universe, but current science has not established that claim experimentally. Many approaches to quantum gravity suggest that ordinary ideas of distance may fail or require modification near that scale, while different models describe the possible limit in different ways. Reviews of minimal length proposals treat the existence and meaning of such a limit as an open theoretical question. not a measured cosmic grid. The Planck length may mark the point where our present theories can no longer be used separately, rather than the size of a final indivisible tile. If space-time ceases to behave smoothly there, something more fundamental might replace it. But even if space turns out to be discrete, its smallest unit would not automatically be the final bottom. The rules connecting those units, the states they can occupy, and the reason those rules exist would remain open to explanation. Finding the smallest measurable distance would answer how finely space can be divided, not why there is a structure capable of having distances at all. The opposite possibility is equally strange. Space and fields may remain continuous, allowing meaningful distinctions at indefinitely smaller scales, even though no physical experiment could resolve them. A limit on measurement is not necessarily a limit on existence. If probing a region requires so much concentrated energy that the experiment radically alters the region, nature may prevent access without proving that nothing lies beyond. You could encounter a permanent horizon of knowledge rather than a final layer of being. There is also no certainty that moving towards smaller scales always means moving toward deeper truth. In some physical descriptions, a system that looks complicated in one set of concepts can be equivalent to a very different description in another. What appears fundamental from one viewpoint may appear emergent from another, while both generate the same observable predictions. If two descriptions are physically equivalent, asking which one contains the real objects may have no experimental answer. Reality might be defined more securely by the relationships and predictions shared between descriptions than by the mental pictures attached to either one. The foundation would then resemble a structure that can be viewed through different languages, none of which owns the final image. This does not mean that all descriptions are equally true, or that science can invent any hidden layer it prefers. A deeper theory must explain existing evidence, preserve the successful predictions of earlier theories where they work, and produce new results that can be tested. The absence of a known bottom is not permission to fill the unknown with fantasy. It is a recognition that every confirmed level has a limited domain, and that no experiment has demonstrated an ultimate substance from which nothing deeper could emerge. There might be a final set of indivisible entities and principles. There might instead be an endless hierarchy, where each apparent foundation becomes the visible behavior of another layer. Or reality may close explanatory loops, in which objects depend on relationships, and relationships depend on the objects they organize, leaving no single component that stands alone as the source of everything else. The demand for a final bottom may arise because the human mind feels safer when explanation reaches something solid. An infinite chain seems incomplete, while a final foundation seems to offer rest. Yet naming a foundation does not end the mystery. If reality ends with particles, you can still ask why those particles and rules exist. If it ends with mathematics, you can ask why that mathematical structure is physically realized. If it ends with information, you can ask what information means without a system in which differences can matter. Every proposed ending creates another form of the question. Perhaps explanation does not terminate in one final object, but becomes a network in which levels support and constrain one another. The universe may not be a tower resting on a lowest stone. It may be more like a pattern whose stability comes from the entire arrangement. You continue downward, expecting the last piece, while nature continues changing what counts as a piece. And the deepest lesson may be that reality does not owe you a final floor, simply because your questions are shaped like falling. There may always be another scale, another description, or another relationship beneath what now appears fundamental. Or the search may eventually reach a point where beneath is no longer a meaningful direction. At that boundary, reality would not become empty. It would become something your inherited concepts of object, size, and composition were never built to hold. Why anything exists at all instead of nothing. The strangest fact you will ever confront is not that the universe is vast, old, or mysterious, but that there is anything here to be mysterious about at all. You can ask why stars form, why matter attracts matter, why living cells organize themselves, or why time seems to move forward. And in each case, science can search for earlier conditions and deeper mechanisms. But the question of why anything exists instead of nothing appears to reach beneath every ordinary explanation, because any answer seems to require that something already be there. A law, a possibility, a cause, a mathematical structure, or a principle capable of producing a universe. Absolute nothing would not be empty space, darkness, silence, or a vacuum. Space would already be something. Time would already allow change. A quantum vacuum would contain fields, rules, and possible states. Even the sentence, "nothing existed," quietly treats nothing as though it were a condition that could last and then be replaced. But if there were truly nothing, no time, no law, no possibility, no distinction between one state and another, there would be no process by which something could begin. This is why claims that the universe came from nothing must be examined carefully. In physics, the word often refers to a vacuum state, a universe with no ordinary particles, or a model without classical space and time. These may be extraordinarily minimal conditions, but they are not philosophical nothingness. They still belong to a framework with rules describing what can happen. Physics can sometimes show how a universe might evolve from a simpler physical state, but that does not automatically explain why the framework, the laws, or the possibility of evolution exists. The question then moves back one level. Why these laws? Why this structure? Why is there a reality capable of containing possibilities at all? One traditional answer is that existence must contain something necessary, something that could not have failed to exist and does not depend on anything deeper. Philosophers have proposed many candidates for this role: a necessary being, necessary laws, logical truth, mathematics, or reality itself. The attraction of such an answer is that it stops the chain of explanation. If something exists by necessity, it does not require a cause in the ordinary sense. Yet the difficulty is showing why the proposed foundation is genuinely necessary, rather than simply being named that way. You can say that the universe exists because a necessary principle produced it, but the mind can still ask why that principle has the form it does, and why it produces this kind of world rather than another. Another possibility is that existence is a brute fact. Reality may exist without a deeper reason, just as a mathematical proof eventually rests on assumptions that are not proven within the same system. This can feel unsatisfying because the human mind is trained to search for causes. When a light turns on, something activated it. When a glass breaks, something struck it. When a person arrives, there is a path explaining how they came. But causal reasoning developed within the universe, where events occur in time and physical states lead to later states. It may not apply to the existence of the whole in the same way. Asking what caused all reality could be like asking what lies earlier than the beginning of time. The grammar of the question may assume a background that the question itself removes. A cause normally comes before its effect, but if time is part of what began, there may be no earlier moment in which a cause could wait. This does not prove that the universe is uncaused. It shows that everyday causation cannot simply be carried beyond its tested domain without difficulty. Cosmology can trace the observable universe toward earlier, hotter, and denser conditions, but the Big Bang model does not by itself explain why existence began. It describes the development of the cosmos from an early state and becomes uncertain under the most extreme conditions. Some models propose a bounce from an earlier phase, an eternally inflating background, cycles of expansion and contraction, or a universe arising through quantum processes. Each proposal attempts to extend the history, but extending history is not the same as explaining why there is a history. An eternal universe would remove a first moment while leaving the existence of the eternal system unexplained. A universe generated by quantum rules would move the question toward the origin of those rules. A multiverse containing every allowed kind of universe might explain why at least one region supports observers, but it would not explain why the multiverse and its possibilities exist. The anthropic principle can tell you that you should not be surprised to observe conditions compatible with observers, because incompatible regions contain no one able to ask the question. But this explains selection within existence, not existence itself. It can help answer why you find yourself in a life-permitting universe, yet it cannot tell you why there are universes available to be selected from. Some thinkers suggest that nothing may be impossible. Perhaps logical consistency, mathematical truth, or possibility itself cannot be absent. If some form of structure exists necessarily, then absolute nothingness was never a genuine alternative. This reverses the original puzzle. Instead of asking why something defeated nothing, you ask why you assumed nothing was the natural default. In ordinary life, an empty box seems simpler than a full one, so the mind imagines nothingness as the simplest possible state. But an empty box requires a box, space, time, and laws maintaining its emptiness. Absolute nothing has no properties, not even simplicity. It cannot be stable, unstable, likely, unlikely, or waiting. Those descriptions already give it structure. Perhaps nothing is not a possible state of reality, but only the absence of a particular thing within an existing framework. You can have no water in a glass, no stars in a region, or no sound in a room. Each absence is defined against something that remains. When you try to remove everything, including the background that makes absence meaningful, language begins to lose its grip. The question may therefore reveal a limit not only in science, but in thought itself. Human concepts were formed to distinguish objects, events, and causes inside an existing world. They may not be equipped to compare existence with absolute non-existence, because no mind has ever encountered nothingness, or could survive to describe it. Yet the inability to answer does not make the question meaningless. It exposes the deepest boundary of explanation. Every scientific answer tells you how one state follows from another. Every historical answer connects one event to earlier events, and every personal answer places a choice inside a larger story. But existence as a whole may not stand inside any larger context from which its reason can be borrowed. There may be a final explanation hidden beyond present understanding, a necessary foundation that future thought will describe more clearly. There may be an endless chain in which every answer opens another question, or there may be no reason beyond the fact that reality exists. Science does not currently decide among these possibilities, and honesty requires leaving the mystery open. What can be said is that nothing in modern physics has demonstrated how absolute nothingness produced something, because absolute nothingness is not a physical state that a theory can easily describe or test. The universe may have emerged from conditions without familiar matter, space, or time, but those conditions would still belong to some form of reality. And perhaps the most profound response is not to pretend the question has been solved, but to recognize what it means that you are able to ask it. A small part of existence has become conscious enough to notice that existence is not self-explanatory. Matter has organized itself into a mind capable of comparing the world with its own absence. Even though absence can never appear before it, you may never discover why there is something rather than nothing. But every question, every breath, and every moment of awareness is already evidence that, for reasons still unknown, possibility did not remain empty, and reality, somehow, is here.